When the Sun became the center, how Copernicus transformed astronomy. Written by Dorothy Stimson, narrated by Jason Zenobia. Dedication. To heretics who question authority. Introduction. David Christopher Lane, Ph.D., Professor of Philosophy. Recently, in my Introduction to Philosophy classes at Mount San Antonio College, one of my brightest students and I got into a heated but fruitful discussion about the role Roman Catholicism played in inhibiting scientific progress, particularly in light of how Galileo and Bruno were treated. This got me thinking anew about the conflict between science and religion. Essentially, most religions believe they already have the revealed truth, and thus all future discoveries must, in some sense, comport with that revelation. Otherwise, the very core of such belief systems can be upended. Witness Christianity's reliance on the Bible and Islam's total acceptance of the Quran. Science, in contrast, doesn't hold to such a priori dogmas, and thus is a new and open-ended quest for understanding how the universe operates. Because of this, it is consistently free to be wrong, and hence it is intrinsically progressive. Where religion remains more or less stagnant, given its already accepted truth claims, science works precisely because it is always changing and adapting to new forms of information that shed a clearer light on previously held maps or paradigms. Therefore, it is not at all surprising that institutions like the Roman Catholic Church has a history of severely slowing down or, on occasion, squelching scientists who unearth findings that appear to contradict their core doctrines. While it is certainly true that Galileo was at times his own worst enemy, witness his disparaging characterizations of the Pope with whom he once had friendly relations, his support of Copernican heliocentrism was regarded as heresy at the time, and thus he was banned from preaching such views. Of course, the Church eventually gave up its Earth-centric notions and formally apologized to Galileo's memory 350 years later. It is an intriguing and instructive chapter in the often tense relationship religion has with science. As Alan Cowell elaborates about the Galileo affair, since then the Church has taken various steps to reverse its opposition to Galileo's conclusions. In 1757, Galileo's Dialogue Concerning the Two Chief World Systems was removed from the Index, a former list of publications banned by the Church. When the latest investigation, conducted by a panel of scientists, theologians and historians, made a preliminary report in 1984, it said that Galileo had been wrongfully condemned. More recently, Pope John Paul II himself has said that the scientist was imprudently opposed. We today know that Galileo was right in adopting the Copernican astronomical theory. Paul Cardinal Poupard, the head of the current investigation, said in an interview published this week. This theory had been presented in a book published in 1543 by the Polish scientist Nicholas Copernicus in opposition to the prevailing theory, advanced by the 2nd-century astronomer Ptolemy, that the Sun and the rest of the cosmos orbited the Earth. But the contest between the two models was purely on theoretic and theological grounds until Galileo made the first observations of the 4 largest moons of Jupiter, exploding the Ptolemaic notion that all heavenly bodies must orbit the Earth. In 1616, the Copernican view was declared heretical because it refuted a strict biblical interpretation of the creation that God fixed the earth upon its foundation, not to be moved forever. But Galileo obtained the permission of Pope Urban VIII, a Barberini and a friend, to continue research into both the Ptolemaic and the Copernican views of the world, provided that his findings drew no definitive conclusions and acknowledged divine omnipotence. But when, in 1632, Galileo published his findings in Dialogue Concerning the Two Chief World Systems, the work was a compelling endorsement of the Copernican system. Summoned to Rome for trial by the Inquisition 1 year later, Galileo defended himself by saying that scientific research and the Christian faith were not mutually exclusive, and that study of the natural world would promote understanding and interpretation of the Scriptures. But his views were judged false and erroneous. Aging, ailing, and threatened with torture by the Inquisition, Galileo recanted on April 30, 1633. Because of his advanced years, he was permitted house arrest in Siena. Legend has it that as Galileo rose from kneeling before his inquisitors, he murmured, "Eppur si muove." Even so, it does move. I think it is vitally important not to forget these pivotal moments in history, since they enlighten us about why it is so important for religion not to interfere with a scientific understanding of the cosmos. Otherwise, we obstruct the greatest pathway for gaining knowledge about how the world really works. It is for this reason that we have taken the first few sections of Dorothy Stimson's brilliant book, The Gradual Acceptance of the Copernican Theory of the Universe, which was first published in 1917, and printed them in a new, compact format. She has provided us with an insightful glimpse into the history of astronomy and how Copernicus in particular, along with Bruno, Galileo, Kepler, and other great thinkers, have transformed our understanding of the solar system that surrounds us. It is a remarkable journey we are on. If science becomes unencumbered by superstition and religious authority, the better off we all are in the process. Chapter 1. The Development of Astronomical Thought to 1400 AD. A preliminary sketch of early theories as a background. The appearances in the heavens have, from earliest historic ages, filled men with wonder and awe. Then they gradually became a source of questioning, and thinkers sought for explanations of the daily and nightly phenomena of sun, moon, and stars. Scientific astronomy, however, was an impossibility until an exact system of chronology was devised. Meanwhile, men puzzled over the shape of the Earth, its position in the universe, what the stars were, and why the positions of some shifted, and what those fiery comets were that now and again appeared and struck terror to their hearts. In answer to such questions, the Chaldean thinkers, slightly before the rise of the Greek schools of philosophy, developed the idea of the seven heavens in their crystalline spheres encircling the earth as their center. This conception seems to lie back of both the later Egyptian and Hebraic cosmologies, as well as of the Ptolemaic. Through the visits of Greek philosophers to Egyptian shores, this conception helped to shape Greek thought, and so indirectly affected Western civilization. Thus, our heritage in astronomical thought, as in many other lines, comes from the Greeks and the Romans reaching Europe, in part through Arabia and Spain, where it was shaped by the influence of the schools, down to the close of the Middle Ages, when men began anew to withstand authority in behalf of observation, and were not afraid to follow whither their reason led them. But not all Greek philosophers, it seems, either knew or accepted the Babylonian cosmology. According to Plutarch, though Thales and later the Stoics believed the earth to be spherical in form, Anaximander thought it to be like a smooth, stony pillar, Anaximenes like a table. Beginning with the followers of Thales or perhaps Parmenides, as Diogenes Laertius claims, a long line of Greek thinkers, including Plato and Aristotle, placed the Earth in the center of the universe. Whether Plato held that the Earth encircled or clung around the axis is a disputed point, but Aristotle claimed it was the fixed and immovable center around which swung the spherical universe with its heaven of fixed stars and its 7 concentric circles of the planets kept in their places by their transparent crystalline spheres. The stars were an even greater problem. Anaximenes thought they were fastened like nails in a crystalline firmament, and others thought them to be fiery plates of gold resembling pictures. But if the heavens were solid, how could the brief presence of a comet be explained? Among the philosophers were some noted as mathematicians whose leader was Pythagoras. He and at least one of the members of his school, Eudoxus, had visited Egypt, according to Diogenes Laertius, and had, in all probability, been much interested in and influenced by the astronomical observations made by the Egyptian priests. On the same authority, Pythagoras was the first to declare the earth was round and to discuss the antipodes. He too emphasized the beauty and perfection of the circle and of the sphere in geometry, forms which became fixed for 2,000 years as the fittest representations of the perfection of the heavenly bodies. There was some discussion in Diogenes' time as to the author of the theory of the Earth's motion of axial rotation. Diogenes gives the honor to Philolaus, one of the Pythagoreans, though he adds that others attribute it to Isetus of Syracuse. Cicero, however, states the position of Isetus of Syracuse as a belief in the absolute fixedness of all the heavenly bodies except the earth, which alone moves in the whole universe, and that its rapid revolutions upon its own axis cause the heavens apparently to move and the earth to stand still. Other thinkers of Syracuse may also have felt the Egyptian influence. For one of the greatest of them, Archimedes, stated the theory of the Earth's revolution around the Sun as enunciated by Aristarchus of Samos. Perhaps this is the hearth fire of the universe around which Philolaus imagined the Earth to whirl. In Arenarius, a curious study on the possibility of expressing infinite sums by numerical denominations, as in counting the sands of the universe, Archimedes writes, "For you have known that the universe is called a sphere by several astrologers, its center the center of the earth, and its radius equal to a line drawn from the center of the sun to the center of the earth. This was written for the unlearned, as you have known from the astrologers." Aristarchus of Samos concludes that the world is many times greater than the estimate we have just given. He supposes that the fixed stars and the sun remain motionless, but that the earth, following a circular course, revolves around the sun as a center, and that the sphere of the fixed stars, having the same sun as a center, is so vast that the circle which he supposes the earth to follow in revolving holds the same ratio to the distance of the fixed stars as the center of a sphere holds to its circumference. These ancient philosophers realized in some degree the immensity of the universe in which the earth was but a point. They held that the earth was an unsupported sphere, the size of which Eratosthenes had calculated approximately. They knew the sun was far larger than the earth, and Cicero, with other thinkers, recognized the insignificance of earthly affairs in the face of such cosmic immensity. They knew, too, about the 7 planets, had studied their orbits, and worked out astronomical ways of measuring the passage of time with a fair amount of accuracy. Hipparchus and other thinkers had discovered the fact of the precession of the equinoxes, though there was no adequate theory to account for it until Copernicus formulated his motion of declination. The Pythagoreans accepted the idea of the Earth's turning upon its axis, and some even held the idea of its revolution around the motionless sun. Others suggested that comets had orbits which they uniformly followed, and therefore their reappearance could be anticipated. Why, then, was the heliocentric theory not definitely accepted? In the first place, such a theory was contrary to the supposed facts of daily existence. A man did not have to be trained in the schools to observe that the earth seemed stable under his feet, and that each morning the sun swept from the east to set at night in the west. Sometimes it rose more to the north or to the south than at other times. How could that be explained if the sun was stationary? Study of the stars was valuable for navigators and for surveyors, perhaps, but such disturbing theories should not be propounded by philosophers. Cleanthes, according to Plutarch, advised that the Greeks ought to have prosecuted Aristarchus the Samian for blasphemy against religion, as shaking the very foundations of the world, because this man, endeavoring to save appearances, supposed that the heavens remained immovable, and that the earth moved through an oblique circle, at the same time turning about its own axis. Few would care to face their fellows as blasphemers and impious thinkers on behalf of an unsupported theory. 1800 years later, Galileo would not do so, even though in his day the theory was by no means unsupported by observation. Furthermore, one of the weaknesses of the Greek civilization militated strongly against the acceptance of this hypothesis so contrary to the evidence of the senses. Experimentation and the development of applied science was practically an impossibility, where the existence of slaves made manual labor degrading and shameful. Men might reason indefinitely, but few, if any, were willing to try to improve the instruments of observation or to test their observations by experiments. At the same time, another astronomical theory was developing which was an adequate explanation for the phenomena observed up to that time. This theory of epicycles and eccentrics, worked out by Apollonius of Perga and by Hipparchus and crystallized for posterity in Ptolemy's great treatise on astronomy, the Almagest, became the fundamental principle of the science until within the last 300 years. The theory of the eccentric was based on the idea that heavenly bodies, following circular orbits, revolved around a center that did not coincide with that of the observer on the Earth. That would explain why the sun appeared sometimes nearer the Earth and sometimes farther away. The epicycle represented the heavenly body as moving along the circumference of one circle, called the epicycle, the center of which moves on another circle, the deferent. With better observation, additional epicycles and eccentrics were used to represent the newly observed phenomena, till in the later Middle Ages the universe became a sphere, with centric and eccentric scribbled o'er, cycle and epicycle, orb in orb. Yet the heliocentric theory was not forgotten. Vitruvius, a famous Roman architect of the Augustan age, discussing the system of the universe, declared that Mercury and Venus, the planets nearest the Sun, moved around it as their center, though the Earth was the center of the universe. This same notion recurs in Marcianus Capella's book in the 5th century AD, and again, somewhat modified, in the 16th century in Tycho Brahe's conception of the universe. Ptolemy devotes a column or two of his Almagest, to use the familiar Arabic name for his Syntaxis Mathematica, to the refutation of the heliocentric theory, thereby preserving it for later ages to ponder on, and for a Copernicus to develop. He admits at the outset that such a theory is only tenable for the stars and their phenomena, and he gives at least 3 reasons why it is ridiculous. If the Earth were not at the center, the observed facts of the seasons and of the day and night would be disturbed and even upset. If the Earth moves, its vastly greater mass would gain in speed upon other bodies, and soon animals and other lighter bodies would be left behind, unsupported in the air, a notion ridiculous to the last degree, as he comments, even to imagine it. Lastly, if it moves, it would have such tremendous velocity that stones or arrows shot straight up in the air must fall to the ground east of their starting point, a laughable supposition indeed to Ptolemy. This book became the great text of the Middle Ages. Its author's name was given to the geocentric theory it maintained. Astronomy for 1,000 years was valuable only to determine the time of Easter and other festivals of the Church, and to serve as a basis for astrology for the mystery-loving people of Europe. To the Arabians in Syria and in Spain belongs the credit of preserving for Europe during this long period the astronomical works of the Greeks, to which they added their own valuable observations of the heavens. Valuable because made with greater skill and better instruments, and because with these observations later scientists could illustrate the permanence or the variability of important elements. They also discovered the so-called trepidation, or apparent shifting of the fixed stars, to explain which they added another sphere to Ptolemy's 8. Early in the 6th century, Uranus translated Aristotle's works into Syrian, and this later was translated into Arabic. Albategnius, the Arabian prince who was the greatest of all their astronomers, made his observations from Arachte and Damascus, checking up and in some cases amending Ptolemy's results. Then the center of astronomical development shifted from Syria to Spain, and mainly through this channel passed on into Western Europe. The scientific fame of Alphonse X of Castile, called the Wise, rests chiefly upon his encouragement of astronomy. With his support, the Alphonsine tables were calculated. He is said to have summoned 50 learned men from Toledo, Cordova, and Paris to translate into Spanish the works of Ptolemy and other philosophers. Under his patronage, the University of Salamanca developed rapidly to become within 200 years one of the 4 great universities of Europe, a center for students from all over Europe and the headquarters for new thought, where Columbus was sheltered and later the Copernican system was accepted and publicly taught at a time when Galileo's views were suppressed. Popular interest in astronomy was evidently aroused, for Sacrobosco, to give John Holywood his better-known Latin name, a Scotch professor at the Sorbonne in Paris in the 13th century, published a small treatise, De Sphere Mundo, that was immensely popular for centuries, though it was practically only an abstract of the Almagest. Whewell tells of a French poem of the time of Edward I entitled Image du Monde, which gave the Ptolemaic view and was illustrated in the manuscripts in the University of Cambridge with a picture of the spherical earth, with men upright on it at every point, dropping balls down perforations in the earth to illustrate the tendency of all things toward the center. Of the same period, the 13th century, is an Arabian compilation in which there is a reference to another work, the Book of Hamamuna the Old, stating that the earth turns upon itself in the form of a circle, and that some are on top, the others below, and there are countries in which it is constantly day, or in which at least the night continues only some instants. Apparently, however, such advanced views were of no influence, and the Ptolemaic theory remained unshaken down to the close of the 15th century. Aside from the adequacy of this explanation of the universe for the times, the attitude of the Church Fathers on the matter were to a large degree responsible for this acquiescence. Early in the 1st century AD, Philo Judaeus emphasized the minor importance of visible objects compared with intellectual matters, a foundation stone in the Church's theory of a homocentric universe. Clement of Alexandria calls the heavens solid, since what is solid is capable of being perceived by the senses. Origen has recourse to the Holy Scriptures to support his notion that the sun, moon, and stars are living beings obeying God's commands. Then Lactantius thunders against those who discuss the universe as comparable to people discussing the character of a city they have never seen and whose name only they know. Such matters cannot be found out by inquiry. The existence of the antipodes and of the rotundity of the earth are marvelous fictions, and philosophers are defending one absurd opinion by another. When in explanation why bodies would not fall off a spherical earth, they claim these are born to the center. How clearly even this brief review illustrates what Henry Osborne Taylor calls the fundamental principles of patristic faith, that the will of God is the one cause of all things, and that this will is unsearchable. He further points out that Augustine's and Ambrose's sole interest in natural fact is as confirmatory evidence of scriptural truth. The great Augustine therefore denies the existence of antipodes, since they could not be peopled by Adam's children. He indifferently remarks elsewhere, "What concern is it to me whether the heavens as a sphere enclose the earth in the middle of the world, or overhang it on either side?" Augustine does, however, dispute the claims of astrologers accurately to foretell the future by the stars, since the fates of twins or those born at the same moment are so diverse. Philastrius, dealing with various heresies, denounces those who do not believe the stars are fixed in the heavens as participants in the vanity of pagans and the foolish opinions of philosophers, and refers to the widespread idea of the part the angels play in guiding and impelling the heavenly bodies in their courses. It would take a brave man to face such attitudes of scornful indifference on the one hand and denunciation on the other, in support of a theory the Church considered heretical. Meanwhile, the Church was developing the homocentric notion which would, of course, presuppose the central position in the universe for man's abiding place. In the Pseudo-Dionysius is an elaborately worked-out hierarchy of the beings in the universe that became the accepted plan of later centuries, best known to modern times through Dante's blending of it with the Ptolemaic theory in the Divine Comedy. Isidore of Seville taught that the universe was created to serve man's purposes, and Peter Lombard in the 12th century sums up the situation in the definite statement that man was placed at the center of the universe to be served by that universe and in turn himself to serve God. Supported by the mighty Thomas Aquinas, this became a fundamental church doctrine. An adequate explanation of the universe existed. Aristotle, Augustine, and the other great authorities of the Middle Ages all upheld the conception of a central earth encircled by the 7 planetary spheres and by the all-embracing starry firmament. In view of the phrases used in the Bible about the heavens, and in view of the formation of fundamental theological doctrines based on this supposition by the Church Fathers, is it surprising that any other than a geocentric theory seemed untenable, to be dismissed with a smile when not denounced as heretical? Small wonder is it, in the absence of the present-day mechanical devices for the exact measurement of time and space as aids to observation, that the Ptolemaic or geocentric theory of the universe endured through centuries as it did, upheld by the authority both of the Church and, in essence at least, by the great philosophers whose works constituted the teachings of the schools. Chapter 2. Copernicus and his Times. During these centuries, one notable scholar at least stood forth in open hostility to the slavish devotion to Aristotle's writings and with hearty appreciation for the greater scientific accuracy of infidel philosophers among the Arabians, Hebrews, and Greeks. In his Opus Tertium in 1267, Roger Bacon also pointed out how inaccurate were the astronomical tables used by the Church. For in 1267, according to these tables, Christians will fast the whole week following the true Easter, and will eat flesh instead of fasting at Quadragesima for a week, which is absurd. And thus Christians are made foolish in the eyes of the heathen. Even the rustic, he added, can observe the phases of the moon occurring a week ahead of the date set by the calendar. Bacon's protests were unheeded, however, and the Church continued using the old tables, which grew increasingly inaccurate with each year. Pope Sixtus IV sought to reform the calendar 2 centuries later with the aid of Regiomontanus, then the greatest astronomer in Europe. The Lateran Council appealed to Copernicus for help in 1514, but little could be done, as Copernicus replied, till the sun's and the moon's positions had been observed far more precisely, and the modern scientific calendar was not adopted until 1582 under Pope Gregory XIII. What was the state of astronomy in the century of Copernicus's birth? Regiomontanus, to use Johann Müller's Latin name, his teacher, Purbach, and the great Cardinal Nicholas of Cues were the leading astronomers of this 15th century. Purbach died before he had fulfilled the promise of his youth, leaving his epitome of Ptolemy's Almagest to be completed by his greater pupil. In his Theorica Planetarum, Purbach sought to explain the motions of the planets by placing each planet between the walls of 2 curved surfaces with just sufficient space in which the planet could move. As M. Delambre remarked, these walls might aid the understanding, but one must suppose them transparent, and even if they guided the planet as was their purpose, they hindered the movement of the comets. Therefore they had to be abandoned, and in our modern physics they are absolutely superfluous. They have even been rather harmful, since they interfered with the slight irregularities caused by the force of attraction in planetary movements which observations have disclosed. This scheme gives some indication of the elaborate devices scholars evolved in order to cope with the increasing number of seeming irregularities observed in the heavens. And perhaps it makes clearer why Copernicus was so dissatisfied with the astronomical hypothesis of his day, and longed for some simpler, more harmonious explanation. Regiomontanus, after Purbach's death, continued his work, and his astronomical tables were in general use throughout Europe till superseded by the vastly more accurate Copernican tables a century later. It has been said that his fame inspired Copernicus, born 3 years before the other's death in 1476, to become as great an astronomer. M. Delambre hails him as the wisest astronomer Europe had yet produced, and certainly his renown was approached only by that of the great cardinal. Both Jansen, the Catholic historian, and Father Hagen of the Vatican Observatory, together with many other Catholic writers, claim that 100 years before Copernicus, Cardinal Nicholas Cusanus had the courage of independence to uphold the theory of the Earth's motion and its rotation on its axis. As Father Hagen remarked, had Copernicus been aware of these assertions, he would probably have been encouraged by them to publish his own monumental work. But the cardinal stated these views of the Earth's motions in a mystical, hypothetical way, which seems to justify the marginal heading, paradox, in the edition of 1565. And, unfortunately for these writers, the Jesuit Father Riccioli, the official spokesman of the order in the 17th century after Galileo's condemnation, speaking of this paradox, called attention also to a passage in one of the cardinal's sermons as indicating that the latter had perhaps forgotten himself in the De Docta Ignorantia, or that this paradox was repugnant to him, or that he had thought better of it. The passage he referred to is as follows: "Prayer is more powerful than all created things. Although angels or some kind of beings move the spheres, the sun, and the stars, prayer is more powerful than they are, since it impedes motion, as when the prayer of Joshua made the sun stand still." This may explain why Copernicus apparently disregarded the cardinal's paradox, for he made no reference to it in his book, and the statement itself, to judge by the absence of contemporary comment, aroused no interest at the time. But of late years, the cardinal's position, as stated in the De Docta Ignorantia, has been repeatedly cited as an instance of the Church's friendly attitude toward scientific thought, to show that Galileo's condemnation was due chiefly to his contumacy and disobedience. Copernicus himself was born in Thorn on February 19, 1473. 7 years after that Hansa town, founded by the Teutonic Order in 1231, had come under the sway of the King of Poland by the Second Peace of Thorn. His father, Nicholas Copernic, was a wholesale merchant of Krakow who had removed to Thorn before 1458, married Barbara Watzelrode of an old patrician Thorn family, and there had served as town councillor for 19 years until his death in 1483. Thereupon his mother's brother, Lucas Watzelrode, later Bishop of Ermeland, became his guardian, benefactor, and close friend. After the elementary training in Thorn School, the lad entered the University of Krakow, his father's former home, where he studied under the Faculty of Arts from 1491 to 1494. Nowhere else north of the Alps at this time were mathematics and astronomy in better standing than at this university. 16 teachers taught these subjects there during the years of Copernicus's stay, but no record exists of his work under any of them. That he must have studied these two sciences there, however, is proved by Rheticus's remark in the Narratio Prima that Copernicus, after leaving Krakow, went to Bologna to work with Dominicus Maria di Novara, non tan disciplus quam adjutor. He left Krakow without receiving a degree, returned to Thorn in 1494 when he and his family decided he should enter the church, after first studying in Italy. Consequently, he crossed the Alps in 1496 and was that winter matriculated at Bologna in the German nation. The following summer he received word of his appointment to fill a vacancy among the canons of the cathedral chapter at Ermeland, where his uncle had been bishop since 1489. He remained in Italy, however, about 10 years altogether, studying civil law at Bologna and canon law and medicine at Padua, yet receiving his degree as Doctor of Canon Law from the University of Ferrara in 1503. He was also in Rome for several months during the Jubilee year 1500. At this period, the professor of astronomy at Bologna was the famous teacher Dominicus Maria di Novara, a man ingenio et animo liber, who dared to attack the immutability of the Ptolemaic system, since his own observations, especially of the pole star, differed by a degree and more from the traditional ones. He dared to criticize the long-accepted system and to emphasize the Pythagorean notion of the underlying harmony and simplicity in nature, and from him Copernicus may have acquired these ideas, for whether they lived together or not in Bologna, they were closely associated. It was here, too, that Copernicus began his study of Greek, which later was to be the means of encouraging him in his own theorizing by acquainting him with the ancients who had thought along similar lines. In the spring of the year 1501, following his visit to Rome, Copernicus returned to the chapter at Frauenburg to get further leave of absence to study medicine at the University of Padua. Whether he received a degree at Padua or not, and how long he stayed there, are uncertain points. He was back in Ermeland early in 1506. His student days were ended, and now for many years he led a very active life, first as companion and assistant to his uncle the bishop, with whom he stayed at Schloss Heilsberg till after the bishop's death in 1512, then as one of the leading canons of the chapter at Frauenburg, where he lived most of the rest of his life. As the chapter representative for 5 years at intervals, he had oversight of the spiritual and temporal affairs of 2 large districts in the care of the chapter. He went on various diplomatic and other missions to the King of Poland, to Duke Albrecht of the Teutonic Order, and to the councils of the German states. He wrote a paper of considerable weight upon the much-needed reform of the Prussian currency. His skill as a physician was in demand, not only in his immediate circle, but in adjoining countries, Duke Albrecht once summoning him to Königsberg to attend one of his courtiers. He was a humanist as well as a Catholic churchman, and though he did not approve of the Protestant revolt, he favored reform and toleration. Gassendi claims that he was also a painter, at least in his student days, and that he painted portraits well received by his contemporaries. But his interest and skill in astronomy must have been recognized early in his life, for in 1514 the committee of the Lateran Council in charge of the reform of the calendar summoned him to their aid. He was no cloistered monk devoting all his time to the study of the heavens, but a cultivated man of affairs, of recognized ability in business and statesmanship, and a leader among his fellow canons. His mathematical and astronomical pursuits were the occupations of his somewhat rare leisure moments, except perhaps during the 6 years with his uncle in the comparative freedom of the bishop's castle, and during the last 10 or 12 years of his life, after his request for a coadjutor had resulted in lightening his duties. In his masterwork, De Revolutionibus, there are recorded only 27 of his own astronomical observations, and these extended over the years from 1497 to 1529. The first was made at Bologna, the second at Rome in 1500, and 7 of the others at Frauenburg, where the rest were also probably made. It is believed the greater part of the De Revolutionibus was written at Heilsberg, where Copernicus was free from his chapter duties, for, as he himself says in the dedication to the Pope, dated 1543, his work had been formulated not merely 9 years, but for more than 3 nines of years. It had not been neglected all this time, however, as the original manuscript, now in the Prague Library, with its innumerable changes and corrections, shows how continually he worked over it, altering and correcting the tables and verifying his statements. Copernicus was a philosopher. He thought out a new explanation of the world machine with relatively little practical work of his own, though we know he controlled his results by the accumulated observations of the ages. His instruments were inadequate, inaccurate, and out of date even in his time, for much better ones were then being made at Nuremberg. And the cloudy climate of Ermeland, as well as his own active career, prevented him from the long-continued, painstaking observing which men like Tycho Brahe were to carry on later. Despite such handicaps, because of his dissatisfaction with the complexities and intricacies of the Ptolemaic system, and because of his conviction that the laws of nature were simple and harmonious, Copernicus searched the writings of the classic philosophers, as he himself tells us, to see what other explanation of the universe had been suggested. And I found first in Cicero that a certain Nicetas had thought the earth moved. Later, in Plutarch, I found certain others had been of the same opinion. He quoted the Greek referring to Philolaus the Pythagorean, Heraclides of Pontus, and Ekphantes the Pythagorean. As a result, he began to consider the mobility of the earth and found that such an explanation seemingly solved many astronomical problems with a simplicity and a harmony utterly lacking in the old traditional scheme. Unaided by a telescope, he worked out in part the right theory of the universe, and for the first time in history placed all the then-known planets in their true positions with the Sun at the center. He claimed that the Earth turns on its axis as it travels around the Sun, and careens slowly as it goes, thus, by these three motions, explaining many of the apparent movements of the Sun and the planets. He retained, however, the immobile heaven of the fixed stars, though vastly farther off in order to account for the non-observance of any stellar parallax, the perfect and therefore circular orbits of the planets, certain of the old eccentrics, and 34 new epicycles in place of all the old ones which he had cast aside. He accepted the false notion of trepidation enunciated by the Arabs in the 9th century and later overthrown by Tycho Brahe. His calculations were weak, but his great book is a sane and modern work in an age of astrology and superstition. His theory is a triumph of reason and imagination, and with its almost complete independence of authority, is perhaps as original a work as a human being may be expected to produce. Copernicus was extremely reluctant to publish his book because of the misunderstandings and malicious attacks it would unquestionably arouse. Possibly, too, he was thinking of the hostility already existing between himself and his bishop Dantiscus, whom he did not wish to antagonize further. But his devoted pupil and friend Rheticus, aided by Tiedemann Giese, Bishop of Culm and a lifelong friend, at length persuaded him. So he entrusted the matter to Giese, who passed it on to Rheticus, then connected with the University of Wittenberg as professor of mathematics. Rheticus, securing leave of absence from Melanchthon, his superior, went to Nuremberg to supervise the printing. This was done by Petreius. Upon his return to Wittenberg, Rheticus left in charge Johann Schörner, a famous mathematician and astronomer, and Andreas Osiander, a Lutheran preacher interested in astronomy. The printed book was placed in Copernicus's hands at Frauenburg on May 24, 1543, as he lay dying of paralysis. Copernicus passed away that day in ignorance that his life's work appeared before the world not as a truth but as an hypothesis, for there had been inserted an anonymous preface stating that this was but another hypothesis for the greater convenience of astronomers. For years, Copernicus was thought to have written this preface to disarm criticism. Kepler, 60 years later in 1601, called attention to this error and quoted Osiander's letters to Copernicus and to Rheticus of May 1541, suggesting that the system be called a hypothesis to avert attacks by theologians and Aristotelians. He claimed that Osiander had written the preface, but Kepler's article never was finished and remained unpublished till 1858. Giese and Rheticus, of course, knew that the preface falsified Copernicus's work, and Geisser, highly indignant at the impiety of the printer, who he thought had written it to save himself from blame, wrote Rheticus, urging him to write another Prefatinunculus, purging the book of this falsehood. This letter is dated July 26, 1543, and the book had appeared in April. Apparently, nothing was done and the preface was accepted without further challenge. It remains to ask whether people other than Copernicus's intimates had known of his theory before 1543. Pucer, Melanchthon's nephew, declared Copernicus was famous by 1525, and the invitation from the Lateran Council Committee indicates his renown as early as 1514. In Vienna, in 1873, there was found a commentariolus, or summary, of his great work, written by Copernicus for the scholars friendly to him. It was probably written soon after 1530 and gives a full statement of his views following a series of 7 axioms, or theses, summing up the new theory. This little book probably occasioned the order from Pope Clement VII in 1533 to Widmanstadt to report to him on the new scheme. This Widmanstadt did in the papal gardens before the Pope with several of the cardinals and bishops, and was presented with a book as his reward. In 1536, the Cardinal Bishop of Capua, Nicholas von Schönberg, apparently with the intent to pave the way for the theory at Rome, wrote for a report of it. It is not known whether the report was sent, and the cardinal died the following year, but that Copernicus was pleased by this recognition is evident from the prominence he gave to the cardinal's letter, as he printed it in his book at the beginning, even before the dedication to the Pope. The most widely circulated account at this time, however, was the Narratio Prima, a letter from Georg Joachim of Rhaetia, better known as Rheticus, written in October 1539 from Frauenburg to Johann Schöner at Nuremberg. Rheticus, at 25 years of age, professor of mathematics at Wittenberg, had gone uninvited to Frauenburg early in that summer to visit Copernicus and learn for himself more in detail about this new system. This was rather a daring undertaking, for not only were Luther and Melanchthon outspoken in their condemnation of Copernicus, but Rheticus was going from Wittenberg, the headquarters of the Lutheran heresy, into the bishopric of Ermeland, where to the bishop and the king his overlord, the very name of Luther was anathema. Nothing daunted, Rheticus departed for Frauenburg and could not speak too highly of the cordial welcome he received from the old astronomer. He came for a few weeks and remained 2 years, to return to Wittenberg as an avowed believer in the system and its first teacher and promulgator. Not only did he write the Narratio Prima and an Encomium Bruci, both extolling Copernicus, but what is more important, he succeeded in persuading him to allow the publication of the De Revolutionibus. Rheticus returned to his post in 1541 to resign it the next year and become Dean of the Faculty of Arts. In all probability, the conflict was too intense between his new scientific beliefs and the statements required of him as professor of the old mathematics and astronomy. His colleague, Erasmus Reinhold, continued to teach astronomy there, though he too accepted the Copernican system. He published a series of tables based on the Copernican calculations to supersede the inaccurate ones by Regiomontanus, and these were in general use throughout Europe for the next 70-odd years. As he himself declared, the series was based in its principles and fundamentals upon the observations of the famous Nicolaus Copernicus. The almanacs deduced from these calculations probably did more to bring the new system into general recognition and gradual acceptance than did the theoretical works. Opposition to the theory had not yet gathered serious headway. There is record of a play poking fun at the system and its originator, written by the Elbing schoolmaster, a Dutch refugee from the Inquisition, and given in 1531 by the villagers at Elbing, 3 miles from Frauenburg. Elbing and Ermeland were hostile to each other. Copernicus was well known in Elbing, though probably from afar, for there seems to have been almost no personal intercourse between canons and people, and the spread of Luther's teachings had intensified the hostility of the villagers toward the Church and its representatives. But not until Giordano Bruno made the Copernican system the starting point of his philosophy was the Roman Catholic Church seriously aroused to combat it. Possibly Osiander's preface turned opposition aside, and certainly the non-acceptance of the system as a whole by Tycho Brahe, the leading astronomer of Europe at that time, made people slow to consider it. Chapter 3. The later development and scientific defense of the Copernican system. Copernicus accomplished much, but even his genius could not far outrun the times in which he lived. When one realizes that not only all the astronomers before him, but he and his immediate successor Tycho Brahe made all their observations and calculations unaided by even the simplest telescope, by logarithms or by pendulum clocks for accurate measurement of time, one marvels, not at their errors, but at the greatness of their genius in rising above such difficulties. This lack of material aids makes the work of Tycho Brahe, accounted one of the greatest observers that has ever lived, as notable in its way perhaps as that of Copernicus. His life was a somewhat romantic one. Born of noble family on December 14, 1546, at Knudstrup in Denmark, Tycho Brahe, the second of 10 children, was early practically adopted by his father's brother. His family wished him to become a statesman and sent him in 1559 to the University of Copenhagen to prepare for that career. A partial eclipse of the sun on August 21, 1560, as foretold by the astronomers, thrilled the lad and determined him to study a science that could foretell the future and so affect men's lives. When he was sent to Leipzig with a tutor in 1562 to study law, he devoted his time and money to the study of mathematics and astronomy. 2 years later, when 18 years of age, he resolved to perform anew the task of Hipparchus and Ptolemy and make a catalogue of the stars more accurate than theirs. His family hotly opposed these plans, and for 6 years he wandered through the German states, now at Wittenberg, now at Rostock, where he fought the duel in which he lost part of his nose and had to have it replaced by one of gold and silver, or at Augsburg, everywhere working on his chosen subjects. But upon his return to Denmark in 1570, he spent 2 years on chemistry and medicine, till the startling appearance of the new star in the constellation of Cassiopeia in November 1572 recalled him to what became his life work. Through the interest and favour of King Frederick II, he was given the island of Hven near Elsinore, with money to build an observatory and the pledge of an annual income from the state treasury for his support. There at Uraniborg from 1576 to 1597, he and his pupils made the great catalogue of the stars and studied comets and the moon. When he was forced to leave Hven by the hostility and the economical tendencies of the young king, after 2 years of wandering he accepted the invitation of the Emperor Rudolphus and established himself at Prague in Bohemia. Among his assistants at Prague was young Johann Kepler, who till Tycho's death on October 24, 1601, was his chief helper for 20 months. And who afterwards completed his observations, publishing the results in the Rudolphine Tables of 1627. This phoenix among astronomers, as Kepler calls him, was the father of modern practical astronomy. He also propounded a third system of the universe, a compromise between the Ptolemaic and the Copernican. In this, the Tychonic system, the Earth is motionless and is the center of the orbits of the Sun, the Moon, and the sphere of the fixed stars, while the Sun is the center of the orbits of the 5 planets. Mercury and Venus move in orbits with radii shorter than the Sun's radius, and the other 3 planets include the Earth within their circuits. This system was in harmony with the Bible and accounted as satisfactorily by geometry as either of the other 2 systems for the observed phenomena. To Tycho Brahe, the Ptolemaic system was too complex and the Copernican absurd. The latter because, to account for the absence of stellar parallax, it left vacant and purposeless a vast space between Saturn and the sphere of the fixed stars, and because Tycho's observations did not show any trace of the stellar parallax that must exist if the Earth moves. Though Tycho thus rejected the Copernican theory, his own proved to be the stepping stone toward the one he rejected, for by it and by his study of comets, he completely destroyed the ideas of solid crystalline spheres to the discredit of the scholastics. And his promulgation of a third theory of the universe helped to diminish men's confidence in authority and to stimulate independent thinking. Copernicus worked out his system by mathematics with but slight aid from his own observations. It was a theory not yet proven true. Tycho Brahe, though denying its validity, contributed in his mass of painstaking, accurate observations the raw material of facts to be worked up by Kepler into the great laws of the planets, attesting the fundamental truth of the Copernican hypothesis. Johann Kepler earned for himself the proud title of lawmaker for the universe, in defiance of his handicaps of ill health, family troubles, and straitened finances. Born in Weil, Württemberg, on December 27, 1571, of noble but indigent parents, he was a sickly child, unable for years to attend school regularly. He finally left the monastery school in Mullefontaine in 1586 and entered the university at Tübingen to stay for 4.5 years. There he studied philosophy, mathematics, and theology. He was a Lutheran, receiving the degree of Master of Arts in 1591. While at the university, he studied under Mestlin, professor of mathematics and astronomy, and a believer in the Copernican theory. Because of Mestlin's teaching, Kepler developed into a confirmed and enthusiastic adherent to the new doctrine. In 1594, he reluctantly abandoned his favorite study, philosophy, and accepted a professorship in mathematics at Graz in Styria. 2 years later, he published his first work, Prodromus Dissertationem Continens Mysterium Cosmographicum, etc., in 1596, in which he sought to prove that the Creator, in arranging the universe, had thought of the 5 regular bodies which can be inscribed in a sphere, according to which he had regulated the order, the number, and the proportions of the heavens and their movements. The book is important not only because of its novelty, but because it gave the Copernican doctrine public explanation and defense. Kepler himself valued it enough to reprint it with his Harmonia Mundi 25 years later, and it won for him appreciative letters from various scientists, notably from Tycho Brahe and Galileo. As Kepler, a Lutheran, was having difficulties in Graz, a Catholic city, he finally accepted Tycho's urgent invitation to come to Prague. He came early in 1600, and after some adjustments had been made between the two, he and his family settled with Tycho that autumn to remain till the latter's death the following November. Kepler himself then held the office of imperial mathematician by appointment for many years thereafter. With the researches of Tycho's lifetime placed at his disposal, Kepler worked out 2 of his 3 great planetary laws from Tycho's observations of the planet Mars. Yet, as Monsieur Bertrand remarks, it was well for Kepler that his material was not too accurate, or its variations, due to the then unmeasured force of attraction, might have hindered him from proving his laws. And luckily for him, the Earth's orbit is so nearly circular that in calculating the orbit of Mars to prove its elliptical form, he could base his work on the Earth's orbit as a circle without vitiating his results for Mars. That a planet's orbit is an ellipse and not the perfect circle was of course a triumph for the new science over the scholastics and Aristotelians, but they had yet to learn what held the planets in their courses. From Kepler's student days under Mestlin, when, as the subject of his disputation, he upheld the Copernican theory, to his death in 1630, he was a staunch supporter of the new teaching. In his Epitome Astronomiae Copernici, he answered objections to it at length. He took infinite pains to convert his friends to the new system. It was in vain that Tycho, on his deathbed, had urged Kepler to carry on their work not on the Copernican, but on the Tychonic scheme. Kepler had reasoned out, according to physics, the laws by which the planets moved. In Italy at this same time, Galileo, with his optic tube invented in 1609, was demonstrating that Venus had phases, even as Copernicus had declared that Jupiter had satellites, and that the moon was scarred and roughened, ocular proof that the old system with its heavenly perfection in number, 7 planets, and in appearance, must be cast aside. Within a year after Galileo's death, Newton was born on January 4, 1643. His demonstration of the universal application of the law of gravitation in 1687 was perhaps the climax in the development of the Copernican system. Complete and final proof was adding in the succeeding years by Romer's discovery of the velocity of light, by Bradley's study of its aberration, by Bessel's discovery of stellar parallax in 1838, and by Foucault's experimental demonstration of the Earth's axial motion with a pendulum in 1851. Chapter 4. Opinions and Arguments in the 16th Century. During the lifetime of Copernicus, Roman Catholic churchmen had been interested in his work. Cardinal Schönberg wrote for full information. Widmanstadt reported on it to Pope Clement VII, and Copernicus had dedicated his book to Pope Paul III. But after his death, the church authorities apparently paid little heed to his theory until some 50 years later, when Giordano Bruno forced it upon their attention in his philosophical teachings. Osiander's preface had probably blinded their eyes to its implications. The Protestant leaders were not quite so urbane in their attitude. While Copernicus was still alive, Luther is reported to have referred to this new astrologer who sought to prove that the earth and not the firmament swung around, saying, "The fool will overturn the whole science of astronomy." But, as the Holy Scriptures state, Joshua bade the sun stand still and not the earth. Melanchthon was more interested in this new idea, perhaps because of the influence of Rheticus, his colleague in the University of Wittenberg and Copernicus's great friend and supporter. But he, too, preferred not to dissent from the accepted opinion of the ages. Informally, in a letter to a friend, he implies the absurdity of the new teaching, and in his Initia Doctrinae Physicae, he goes to some pains to disprove the new assumption, not merely by mathematics, but by the Bible, though with a kind of apology to other physicists for quoting the divine witness. He refers to the phrase in Psalm 19, likening the sun in its course to a strong man about to run a race, proving that the sun moves. Another psalm states that the earth was founded not to be moved for eternity, and a similar phrase occurs in the 1st chapter of Ecclesiastes. Then there was the miracle when Joshua bade the sun stand still. While this is a sufficient witness to the truths, there are other proofs. First, in the turning of a circumference, the center remains motionless. Next, changes in the length of the day and of the seasons would ensue were the position of the Earth in the universe not central, and it would not be equidistant from the two poles. He has previously disposed of infinity by stating that the heavens revolve around the pole, which could not happen if a line drawn from the center of the universe were infinitely projected. Furthermore, the Earth must be at the center for its shadow to fall upon the moon in an eclipse. He refers next to the Aristotelian statement that to a simple body belongs one motion. The Earth is a simple body, therefore it can have but one motion. What is true of the parts applies to the whole. All the parts of the Earth are borne toward the Earth and their rest. Therefore the whole Earth is at rest. Quiet is essential to growth. Lastly, if the Earth moved as fast as it must if it moves at all, everything would fly to pieces. Melanchthon sums up the usual arguments from the scriptures, from Aristotle, Ptolemy, and then the current physics in opposition to this theory. Not only did he publish his own textbook on physics, but he republished Sacrobosco's famous introduction to astronomy, writing for it a preface urging diligent study of this little text endorsed by so many generations of scholars. Calvin, the great teacher of the Protestant revolt, apparently was little touched by this new intellectual current. He did write a semi-popular tract against the so-called judicial astrology, then widely accepted, which he, like Luther, condemns as a foolish superstition, though he values la vraie science d'astrologie, from which men understand not merely the order and place of the stars and planets, but the causes of things. In his commentaries, he accepts the miracle of the sun's standing still at Joshua's command as proof of the faith Christ commended, so strong that it will remove mountains. And he makes reference only to the time-honored Ptolemaic theory in his discussion of Psalm 19. For the absolute authority of the Pope, the Protestant leaders substituted the absolute authority of the Bible. It is not strange, then, that they ignored or derided a theory as yet unsupported by proof and so difficult to harmonize with a literally accepted Bible. How widespread among the people generally did this theory become in the years immediately following the publication of the De Revolutionibus? Monsieur Flammarion, in his Vie de Copernic, refers to the famous clock in the Strasbourg Cathedral as having been constructed by the University of Strasbourg in protest against the action taken by the Holy Office against Galileo, though the clock was constructed in 1571 and Galileo was not condemned until 1633. This astronomical clock, constructed only 30 years after the death of Copernicus, he claims represented the Copernican system of the universe, with the planets revolving around the sun, and explained clearly in the sight of the people what was the thought of the makers. Lest no one should miscomprehend, he adds, the portrait of Copernicus was placed there with this inscription: Nicolae Copernici vera effigies ex ipsius autographo depicta. This would be important evidence of the spread of the theory, were it true. But Monsieur Flammarion must have failed to see a brief description of the Strasbourg clock written in 1856 by Charles Schwilge, son of the man who renovated its mechanism in 1838 to 1842. He describes the clock as it was before his father made it over and as it is today. Originally constructed in 1352, it was replaced in 1571 by an astrolabe based on the Ptolemaic system. 6 hands with the zodiacal signs of the planets gave their daily movements and, together with a 7th representing the sun, revolved around a map of the world. When Monsieur Schwilge repaired the clock in 1838, he changed it to harmonize with the Copernican system. But within 18 years after the publication of the De Revolutionibus, proof of its influence is to be found in such widely separated places as London and the great Spanish University of Salamanca. In 1551, Robert Record, court physician to Edward and to Mary and teacher of mathematics, published in London his Castle of Knowledge, an introduction to astronomy and the first book printed in England describing the Copernican system. He evidently did not consider the times quite ripe for a full avowal of his own allegiance to the new doctrine, but the remarks of the Meister and Scholar are worth repeating. Meister. Howbeit Copernicus, a man of great learning, of much experience, and of wonderful diligence in observation, hath renewed the opinion of Aristarchus Samius, affirming that the earth not only moveth circularly about his own centre, but also may be, yea, and is, continually out of the precise centre of the world, 38,000 miles. But because the understanding of that controversy depends of profounder knowledge than in this introduction may be uttered conveniently, I will let it pass till some other time. Scholar. Nay, sit in good faith. I desire not to hear such vain fantasies, so far against the common reason and repugnant to the content of all the learned multitude of writers, and therefore let it pass for ever and a day longer. Meister. You are too young to be a good judge in so great a matter. It passeth far your learning, and theirs also that are much better learned than you, to improve his supposition by good arguments, and therefore you were best condemn nothing that you do not well understand. But another time, as I said, I will so declare his supposition that you shall not only wonder to hear it, but also peradventure be as earnest then to credit it as you are now to condemn it. In the mean season let us proceed forward in our former order. This little book, reprinted in 1556 and in 1596, and one of the most popular of the mathematical writings in England during that century, must have interested the English in the new doctrine even before Bruno's emphatic presentation of it to them in the 80s. Yet the English did not welcome it cordially. One of the most popular books of this period was Sylvester's translation of Du Bartas's The Divine Weeks, which appeared in France in 1578, a book loved especially by Milton. Du Bartas writes, "Those clerks that think how absurd a jest, that neither heavens nor stars do turn at all, nor dance around this great round earthly ball. But the earth itself, this massy globe of ours, turns round about once every 12 hours, and we resemble land-bred novices, new brought aboard to venture on the seas, who at first launching from the shore suppose the ship stands still, and that the firm earth goes." Quite otherwise was the situation in the 16th century at the University of Salamanca. A new set of regulations for the university, drawn up at the king's order by Bishop Covarrubias, was published in 1561. It contained the provision in the curriculum that mathematics and astrology are to be given in 3 years. The first, astrology; the second, Euclid, Ptolemy, or Copernicus ad vota audientium, which also indicates, as Vicente de la Fuente points out, that at this university the choice of the subject matter to be taught lay not with the teachers, but with the students, a rare situation. One wonders what happened there when the professors and students received word from the Cardinal Nuncio at Madrid in 1633 that the congregations of the Index had decreed the Copernican doctrine was thereafter in no way to be held, taught, or defended. One of the graduates of this university, Father Zuniga, better known as Didacus Ars Tunica, wrote a commentary on Job that was licensed to be printed in 1579, but was not published until 1584 at Toledo. Another edition appeared at Rome 7 years later. It evidently was widely read, for it was condemned donec corrugata by the Index in 1616, and the mathematical literature of the next half-century contains many allusions to his remarks on Job 9:6. Who shaketh the earth out of her place, and the pillars thereof tremble? After commenting here upon the greater clarity and simplicity of the Copernican theory, Didacus R. Stunica then states that the theory is not contradicted by Solomon in Ecclesiastes, as that text signifieth no more but this, that although the succession of ages and generations of men on earth be various, yet the earth itself is still one and the same, and continueth without any sensible variation. And it hath no coherence with its context, as philosophers show, if it be expounded to speak of the earth's immobility. The motion that belongs to the earth by way of speech is assigned to the sun, even by Copernicus himself, and those who are his followers. To conclude, no place can be produced out of Holy Scriptures which so clearly speaks the earth's immobility, as this doth its mobility. Therefore this text of which we have spoken is easily reconciled to this opinion, and to set forth the wonderful power and wisdom of God, who can endue the frame of the whole earth, it being of monstrous weight by nature, with motion, this our divine penman added, and the pillars thereof tremble, as if he would teach us from the doctrine laid down that it is moved from its foundations. French thinkers, like the English, did not encourage the new doctrine at this time. Montaigne was characteristically indifferent. What shall we reap by it, but only that we need not care which of the two it be? And who knoweth whether 100 years hence a third opinion will arise, which happily shall overthrow these two precedent? The famous political theorist Jean Bodin was as thoroughly opposed to it as Du Bartas had been. In the last year of his life, Bodin wrote his Universae Naturae Theatruum, in which he discussed the origin and composition of the universe and of the animal, vegetable, mineral, and spiritual kingdoms. These 5 books or divisions reveal his amazing ideas of geology, physics, and astronomy, while at the same time they show a mind thoroughly at home in Hebrew and Arabian literature as well as in the classics. His answer to the Copernican doctrine is worth quoting to illustrate the attitude of one of the keenest thinkers in a brilliant era. Theorist: since the sun's heat is so intense that we read it has sometimes burned crops, houses, and cities in Scythia, would it not be more reasonable that the sun is still and the earth indeed revolves? Mystic: such was the old idea of Philolaus, Timaeus, Ecphantes, Seleucus, Aristarchus of Samos, Archimedes, and Eudoxus, which Copernicus has renewed in our time. But it can easily be refuted by its shallowness, although no one has done it thoroughly. Theorist: what arguments do they rely on who hold that the earth is revolved and that the sun, forsooth, is still? Mystic: because the comprehension of the human mind cannot grasp the incredible speed of the heavenly spheres, and especially of the 10th sphere, which must be 10 times greater than that of the 8th, for in 24 hours it must traverse 469,562,845 miles, so that the earth seems like a dot in the universe. This is the chief argument. Besides this, we get rid entirely of epicycles in representing the motions of the planets, and what is taught concerning the motion of trepidation in the 8th sphere vanishes. Also, there is no need for the 9th and 10th spheres. There is one argument which they have omitted, but which seems to be more efficacious than any, viz., rest is nobler than movement, and that celestial and divine things have a stable nature, while elemental things have motion, disturbance, and unrest. Therefore, it seems more probable that the latter move rather than the former. But while serious absurdities result from the idea of Eudoxus, far more serious ones result from that of Copernicus. Theorist. What are these absurdities? Mystic. Eudoxus knew nothing of trepidation, so his idea seems to be less in error. But Copernicus, in order to uphold his own hypothesis, claims the Earth has three motions, its diurnal and annual ones, and trepidation. If we add to these the pull of weight towards the center, we are attributing 4 natural motions to one and the same body. If this is granted, then the very foundations of physics must fall into ruins, for all are agreed upon this, that each natural body has but one motion of its own, and that all others are said to be either violent or voluntary. Therefore, since he claims the Earth is agitated by 4 motions, one can only be its own. The others must be confessedly violent, yet nothing violent in nature can endure continuously. Furthermore, the Earth is not moved by water, much less by the motion of air or fire in the way we have stated the heavens are moved by the revolutions of the enveloping heavens. Copernicus further does not claim that all the heavens are immobile, but that some are moved, that is, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. But why such diversity? No one, in his senses or imbued with the slightest knowledge of physics, will ever think that the Earth, heavy and unwieldy from its own weight and mass, staggers up and down around its own centre and that of the Sun, for at the slightest jar of the Earth we would see cities and fortresses, towns and mountains thrown down. A certain courtier, Orlicus, when some astrologer in court was upholding Copernicus's idea before Duke Albert of Prussia, turning to the servant who was pouring the Falernian, said, "Take care that the flagon is not spilled, for if the Earth were to be moved, neither an arrow shot straight up, nor a stone dropped from the top of a tower would fall perpendicularly, but either ahead or behind." With this argument, Ptolemy refuted Eudoxus. But if we search into the secrets of the Hebrews and penetrate their sacred sanctuaries, all these arguments can easily be confirmed. For when the Lord of Wisdom said the sun swept in its swift course from the eastern shore to the west, he added this, "Terra vero stat aeternum." Lastly, all things, on finding places suitable to their natures, remain there, as Aristotle writes. Since therefore the Earth has been allotted a place fitting its nature, it cannot be whirled around by other motion than its own. Theorist. I certainly agree to all the rest with you, but Aristotle's law, I think, involves a paralogism. For by this argument the heavens should be immobile, since they are in a place fitting their nature. Mystic. You argue subtly indeed, but in truth this argument does not seem necessary to me. For what Aristotle admitted, that, while forsooth all the parts of the firmament changed their places, the firmament as a whole did not, is exceedingly absurd. For either the whole heaven is at rest, or the whole heaven is moved. The senses themselves disprove that it is at rest, therefore it is moved. For it does not follow that if a body is not moved away from its place, it is not moved in that place. Furthermore, since we have the most certain proof of the movement of trepidation, not only all the parts of the firmament, but also the 8 spheres must necessarily leave their places and move up and down, forward and back. This was the opinion of a profound thinker and experienced man of affairs living when Tycho Brahe and Bruno were still alive, and Kepler and Galileo were beginning their astronomical investigations. But he was not alone in his views, as we shall see, for at the close of the 16th century the Copernican doctrine had few avowed supporters. The Roman Church was still indifferent. The Protestants, clinging to the literal interpretation of the Bible, were openly antagonistic. The professors as a whole were too Aristotelian to accept or pay much attention to this novelty, except Kepler and his teacher Mestlin, though the latter refused to uphold it in his textbook, while astronomers and mathematicians who realized the insuperable objections to the Ptolemaic conception welcomed the Tychonic system as a via media, and the common folk, if they heard of it at all, must have ridiculed it because it was so plainly opposed to what they saw in the heavens every day. In the same way, their intellectual superiors exclaimed at the delirium of those supporting such a notion. One thinker, however, was to see far more in the doctrine than Copernicus himself had conceived, and by Giordano Bruno the Roman Church was to be aroused. Chapter 5. Bruno and Galileo. When the Roman Catholic authorities awoke to the dangers of the new teaching, they struck with force. The first to suffer was the famous monk-philosopher Giordano Bruno, whose trial by the Holy Office was premonitory of trouble to come for Galileo. After an elementary education at Naples near his birthplace, Nola, Filippo Bruno entered the Dominican monastery in 1562 or 1563 when about 14 years old, assuming the name Giordano at that time. Before 1572, when he entered the priesthood, he had fully accepted the Copernican theory, which later became the basis of all his philosophical thought. Bruno soon showed he was not made for the monastic life. Various processes were started against him, and fleeing to Rome, he abandoned his monk's garments and entered upon the 16 years of wandering over Europe, a peripatetic teacher of the philosophy of an infinite universe as deduced from the Copernican doctrine, and thus, in a way, its herald. He reached Geneva in 1579, where he did not accept Calvinism as was formerly thought, but decided before many months had passed that it was wise to depart elsewhere because of the unpleasant position in which he found himself there. He had been brought before the council for printing invectives against one of the professors, pointing out some 20 of his errors. The council sent him to the consistory, the governing body of the church, where a formal sentence of excommunication was passed against him. When he apologized, it was withdrawn. Probably a certain stigma remained, and he left Geneva soon thereafter with a warm dislike for Calvinism. After lecturing at the University of Toulouse, he appeared in Paris in 1581, where he held an extraordinary readership. 2 years later, he was in England, for he lectured at Oxford during the spring months and defended the Copernican theory before the Polish Prince Alasco during the latter's visit there in June. To Bruno belongs the glory of the first public proclamation in England of the new doctrine, though only Gilbert and possibly Wright seem to have accepted it at the time. Upon Bruno's return to London, he entered the home of the French ambassador as a kind of secretary, and there spent the happiest years of his life till the ambassador's recall in October 1585. It was during this period that he wrote some of his most famous books. In La Cena della Cenere, he defended the Copernican theory, incidentally criticizing the Oxford dons most severely, for which he apologized in De la Causa Principio et Uno. He developed his philosophy of an infinite universe in Del Infinito Immundi, and in the Spazio della Bestia Trionfante attacked all religions of mere credulity as opposed to religions of truth and deeds. This last book was at once thought to be a biting attack upon the Roman Church, and later became one of the grounds of the Inquisition's charges against him. During this time in London also, he came to know Sir Philip Sidney intimately, and Fulk Greville, as well as others of that brilliant period. He may have known Bacon, but it is highly improbable that he and Shakespeare met, or that Shakespeare ever was influenced by the other's philosophy. Leaving Paris soon after his return thither, Bruno wandered into southern Germany. At Marburg he was not permitted to teach, but at Wittenberg the Lutherans cordially welcomed him into the university. After a stay of a year and a half, he moved on to Prague for a few months, then to Helmstadt, Frankfurt, and Zurich, and back to Frankfurt again, where, in 1591, he received an invitation from a young Venetian patrician, Messenigo, to come to Venice as his tutor. He re-entered Italy, therefore, in August, much to the amazement of his contemporaries. It is probable that Messenigo was acting for the Inquisition. At any rate, he soon denounced Bruno to that body, and in May 1592 surrendered him to it. In his trial before the Venetian Inquisition, Bruno told the story of his life and stated his belief in answer to the charges against him, based mainly on travesties of his opinions. In this statement, as well as in La Cena della Cenere and in De Immenso de Innumerabilis, Bruno shows how completely he had not merely accepted the Copernican doctrine, but had expanded it far beyond its author's conception. The universe, according to Copernicus, though vastly greater than that conceived by Aristotle and Ptolemy, was still finite because enclosed within the sphere of the fixed stars. Bruno declared that not only was the Earth only a lesser planet, but this world itself was merely one of an infinite number of particular worlds similar to this, and that all planets and other stars are infinite worlds without number, composing an infinite universe, so that there is a double infinitude, that of the greatness of the universe and that of the multitude of worlds. How important this would be to the church authorities may be realized by recalling the patristic doctrine that the universe was created for man and that his home is its center. Of course, their cherished belief must be defended from such an attack, and, naturally enough, the Copernican doctrine as the starting point of Bruno's theory of an infinite universe was thus brought into question. For, as M. Berti has said, Bruno's doctrine was equally an astrotheology, or a theological astronomy. The Roman Inquisition was not content to let the Venetian court deal with this arch-heretic, but wrote in September 1592 demanding his extradition. The Venetian body referred its consent to the state for ratification, which the Doge and council refused to grant. Finally, when the papal nuncio had represented that Bruno was not a Venetian but a Neapolitan, and that cases against him were still outstanding both in Naples and at Rome, the state consented, and in February of the next year Bruno entered Rome, a prisoner of the Inquisition. Nothing further is known about him until the congregations took up his case on February 4th, 1599. Perhaps Pope Clement had hoped to win back to the true faith this prince of heretics. However, Bruno stood firm, and early in the following year he was degraded, sentenced, and handed over to the secular authorities, who burned him at the stake in the Campo di Fiori, February 17, 1600. All his books were put on the index by a decree of February 8, 1600, where they remain to this day, and as a consequence they became extremely rare. It is well to remember Bruno's fate when considering Galileo's case, for Galileo was at that time professor of mathematics at the University of Padua and fully cognizant of the event. Galileo's father, though himself a skilled mathematician, had intended that his son, born at Pisa February 15, 1564, should be a cloth dealer, but at length permitted him to study medicine instead at the University of Pisa, after an elementary education at the monastery at Vallombrosa near Florence. At the Tuscan court in Pisa, Galileo received his first lesson in mathematics, which thereupon became his absorbing interest. After nearly 4 years, he withdrew from the university to Florence and devoted himself to that science and to physics. His services as a professor at this time were refused by 5 of the Italian universities. Finally, in 1589, he obtained the appointment to the chair of physics at Pisa. He became so unpopular there, however, through his attacks on the Aristotelian physics of the day, that after 3 years he resigned and accepted a similar position at Padua. He remained here nearly 18 years, till his longing for leisure in which to pursue his researches and the patronage of his good friend, the Grand Duke of Tuscany, brought him a professorship at the University of Pisa again, this time without obligation of residence nor of lecturing. He took up his residence in Florence in 1610 and, later in 1626, purchased a villa at Arcetri outside the city in order to be near the convent where his favourite daughter, Sor Maria Celeste, was a religious. During the greater part of his lectureship at Padua, Galileo taught according to the Ptolemaic cosmogony out of compliance with the popular feeling, though himself a Copernican. In a letter to Kepler, August 4, 1597, he speaks of his entire acceptance of the new system for some years, but not until after the appearance of the new star in the heavens in 1604 and 1605, and the controversy that its appearance aroused over the Aristotelian notion of the perfect and unchangeable heavens, did he publicly repudiate the old scheme and teach the new. The only information we have as to how he came to adopt the Copernican scheme for himself is the account given by Sagredo, Galileo's spokesman in the famous Dialogue on the Two Principal Systems, 1632. Being very young and having scarcely finished my course of philosophy which I left off, as being set upon other employments, there chanced to come into these parts a certain foreigner of Rostock, whose name as I remember was Christianus Vostitius, a follower of Copernicus, who in an academy made 2 or 3 lectures upon this point, to whom many flocked as auditors. But I, thinking they went more for the novelty of the subject than otherwise, did not go to hear him, for I had concluded with myself that that opinion could be no other than a solemn madness. And, questioning some of those who had been there, I perceived they all made a jest thereof, except one, who told me that the business was not altogether to be laughed at. And because this man was reputed by me to be very intelligent and wary, I repented that I was not there, and began from that time forward, as oft as I met with anyone of the Copernican persuasion, to demand of them if they had always been of the same judgment. And of as many as I examined, I found not so much as one who told me not that he had been a long time of the contrary opinion, but to have changed it for this, as convinced by the reasons proving the same. And afterwards, questioning them one by one, to see whether they were well possessed of the reasons of the other side, I found them all to be very ready and perfect in them, so that I could not truly say they had took up this opinion out of ignorance, vanity, or to show the acuteness of their wits. On the contrary, of as many of the Peripatetics and Ptolemaics as I have asked, and out of curiosity I have talked with many, what pains they had taken in the book of Copernicus, I found very few that had so much as superficially perused it. But of those whom, I thought, had understood the same, not one. And, moreover, I have inquired amongst the followers of the Peripatetic doctrine, if ever any of them had held the contrary opinion, and likewise found that none had. Whereupon, considering that there was no man who followed the opinion of Copernicus that had not been first on the contrary side, and that was not very well acquainted with the reasons of Aristotle and Ptolemy, and on the contrary, that there is not one of the followers of Ptolemy that had ever been of the judgment of Copernicus, and that had left that to embrace this of Aristotle, Considering, I say, these things, I began to think that one who leaveth an opinion imbued with his milk, and followed by very many, to take up another owned by very few, and denied by all the schools, and that really seems a very great paradox, must needs have been moved, not to say forced, by more powerful reasons. For this cause, I am become very curious to dive, as they say, into the bottom of this business, and bring myself to a certainty in this subject. Galileo's brilliant work in mechanics and his great popularity, for his lectures were thronged, combined with his skilled and witty attacks upon the accepted scientific ideas of the age, embittered and antagonized many who were both conservative and jealous. The Jesuits particularly resented his influence and power, for they claimed the leadership in the educational world and were jealous of intruders. Furthermore, they were bound by the decree of the 50th General Congregation of their society in 1593 to defend Aristotle, a decree strictly enforced. While a few of the Jesuits were friendly disposed to Galileo at first, the controversies in which he and they became involved and their bitter attacks upon him made him feel by 1633 that they were among his chief enemies. Early in 1609, Galileo heard a rumour of a spy-glass having been made in Flanders, and proceeded to work one out for himself according to the laws of perspective. The fifth telescope that he made magnified 30 diameters, and it was with such instruments of his own manufacture that he made in the next 3 years his famous discoveries. Jupiter's 4 satellites, which he named the Medicean planets, Saturn's tripartite character, the rings were not recognized as such for several decades thereafter, the stars of the Milky Way, the crescent form of Venus, the mountains of the moon, many more fixed stars, and the spots on the sun. Popular interest waxed with each new discovery, and from all sides came requests for telescopes. Yet there were those who absolutely refused even to look through a telescope, lest they be compelled to admit Aristotle was mistaken. And others claimed that Jupiter's moons were merely defects in the instrument. The formal announcement of the first of these discoveries was made in the Sidereus Nuncius, 1610. A book that aroused no little opposition. Kepler, however, had it reprinted at once in Prague with a long, appreciative preface of his own. The following March, Galileo went to Rome to show his discoveries, and was received with the utmost distinction by princes and church dignitaries alike. A commission of 4 scientific members of the Roman College had previously examined his claims at Cardinal Bellamine's suggestion, and had admitted their truth. Now Pope Paul V gave him long audiences. The Accademia dei Lincei elected him a member, and everywhere he was acclaimed. Nevertheless, his name appears on the secret books of the Holy Office as early as May of that year, 1611. Already he was a suspect. His Della Macchiae Solari, 1611, brought on a sharp contest over the question of priority of discovery between him and the Jesuit father Christopher Scheiner of Ingolstadt, from which Galileo emerged victorious and more disliked than before by that order. Opposition was becoming active. Father Castelli, for instance, the professor of mathematics at Pisa and Galileo's intimate friend, was forbidden to discuss in his lectures the double motion of the earth, or even to hint at its probability. This same father wrote to his friend early in December 1613 to tell him of a dinner-table conversation on this matter at the Tuscan court, then wintering at Pisa. Castelli told how the Dowager Grand Duchess Christina had had her religious scruples aroused by a remark that the Earth's motion must be wrong because it contradicted the Scriptures, a statement that he had tried to refute. Galileo wrote in reply, December 21, 1613, the letter that was to cause him endless trouble, in which he marked out the boundaries between science and religion, and declared it a mistake to take the literal interpretation of passages in Scripture that were obviously written according to the understanding of the common people. He pointed out, in addition, how futile the miracle of the sun's standing still was as an argument against the Copernican doctrine, for, even according to the Ptolemaic system, not the sun, but the primum mobile must be stayed for the day to be lengthened. Father Castelli allowed others to read and to copy this supposedly private letter. Copies went from hand to hand in Florence, and discussion ran high. On the fourth Sunday in December 1614, Father Caccini of the Dominicans preached a sermon in the church of S.M. Novella on Joshua's miracle, in which he sharply denounced the Copernican doctrine taught by Galileo as heretical, so he believed. The Copernicans found a Neapolitan Jesuit who replied to Caccini the following Sunday from the pulpit of the Duomo. In February 1615 came the formal denunciation of Galileo to the Holy Office at Rome by Father Lorini, a Dominican associate of Caccini's at the convent San Marco. The father sent with his friendly warning a copy of the letter to Castelli, charging that it contained many propositions which were either suspect or temerarious, and, he added, though the Galliesti were good Christians, they were rather stubborn and obstinate in their opinions. The machinery of the Inquisition began secretly to turn. The authorities failed to get the original letter, for Castelli had returned that to Galileo at the latter's request. Pope Paul sent word to Father Caccini to appear before the Holy Office in Rome to depose on this matter of Galileo's errors, pro exoneratione sue conscientiae. This he did freely in March, and was, of course, sworn to secrecy. He named a certain nobleman, a Copernican, as the source of his information about Galileo, for he did not know the latter even by sight. This nobleman was, by order of the Pope, examined in November, after some delay by the Inquisitor at Florence. His testimony was to the effect that he considered Galileo the best of Catholics. Meanwhile, the consultors of the Holy Office had examined Lorini's copy of the letter and reported the finding of only 3 objectionable places, all of which, they stated, could be amended by changing certain doubtful phrases. Otherwise it did not deviate from the true faith. It is interesting to note that the copy they had differed in many minor respects from the original letter, and in one place heightened a passage with which the examiners found fault as imputing falsehood to the Scriptures, although they are infallible. Galileo's own statement ran that there were many passages in the Scriptures which, according to the literal meaning of the words, hanno aspetto diverso dal vero, the copy read, molte proposizione falso quanto al nudo senso delle parole. Rumors of trouble reached Galileo, and, urged on by his friends, in 1615 he wrote a long, formal elaboration of the earlier letter, addressing this one to the Dowager Grand Duchess, but he had only added fuel to the fire. At the end of the year he voluntarily went to Rome, regardless of any possible danger to himself, to see if he could not prevent a condemnation of the doctrine. It came as a decided surprise to him to receive an order to appear before Cardinal Bellarmine on February 26, 1616, and there to learn that the Holy Office had already condemned it 2 days before. He was told that the Holy Office had declared, first, that the proposition that the sun is the center of the universe and is immobile is foolish and absurd in philosophy and formally heretical, since it contradicts the express words of the Scriptures in many places according to the meaning of the words and the common interpretation and sense of the fathers and the doctors of theology. And, secondly, that the proposition that the earth is not the center of the universe, nor immobile, receives the same censure in philosophy and in regard to its theological truth. It at least is erroneous in faith. Exactly what was said at that meeting between the two men became the crucial point in Galileo's trial 16 years later. Hence, a somewhat detailed study is important. At the meeting of the congregation on February 25th, the Pope ordered Cardinal Bellarmine to summon Galileo and, in the presence of a notary and witnesses lest he should prove recusant, warn him to abandon the condemned opinion and in every way to abstain from teaching, defending, or discussing it. If he did not acquiesce, he was to be imprisoned. The secret archives of the Vatican contain a minute reporting this interview dated February 26, 1616, in which the cardinal is said to have ordered Galileo to relinquish this condemned proposition, and that Galileo promised to obey. Rumors evidently were rife in Rome at the time as to what had happened at this secret interview, for Galileo wrote to the cardinal in May asking for a statement of what actually had occurred so that he might silence his enemies. The cardinal replied, "We, Robert Cardinal Bellarmine, having heard that Signor Galileo was calumniated and charged with having abjured in our hand and also of being punished by salutary penance, and being requested to give the truth, state that the aforesaid Signor Galileo has not abjured in our hand, nor in the hand of any other person in Rome, still less in any other place, so far as we know, any of his opinions and teachings, nor has he received salutary penance, nor any other kind. But only was he informed of the declaration made by His Holiness and published by the Sacred Congregation of the Index, in which it is stated that the doctrine attributed to Copernicus, that the earth moves around the sun and that the sun stands in the center of the world without moving from the east to the west, is contrary to the Holy Scriptures and therefore cannot be defended nor held. And in witness of this, we have written and signed these presents with our own hand, this 26th day of May, 1616. Robert Cardinal Bellarmine. Galileo's defense 16 years later was that he had obeyed the order as given him by the cardinal, and that he had not defended nor held the doctrine in his Dialogi, but had refuted it. The congregation answered that he had been ordered not only not to hold nor defend, but also not to treat in any way this condemned subject. When Galileo disclaimed all recollection of that phrase and produced the cardinal's statement in support of his position, he was told that this document, far from lightening his guilt, greatly aggravated it, since he had dared to deal with a subject that he had been informed was contrary to the Holy Scriptures. To return to 1616. On the 3rd of March, the cardinal reported to the congregation in the presence of the Pope that he had warned Galileo, and that Galileo had acquiesced. The congregation then reported its decree suspending, until corrected, Nicolae Copernici de Revolutionibus Orbium Coelestum et Didacti Astunica in Job, and prohibiting Epistola Fratris Pauli Antonii Foscarini Carmeliti, together with all other books dealing with this condemned and prohibited doctrine. The Pope ordered this decree to be published by the Master of the Sacred Palace, which was done 2 days later. But this prohibition could not have been widely known for 2 or 3 years. The next year, Muller published his edition of the De Revolutionibus at Amsterdam without a word of reference to it. In 1618, Thomas Fayens, professor at Louvain, heard vague rumours of the condemnation and wondered if it could be true, and the following spring, Fromundus, also at Louvain, and later a noted antagonist of the new doctrine, wrote to Fayens, asking, "What did I hear lately from you about the Copernicans? That they have been condemned a year or two ago by our Holy Father Pope Paul V? Until now I have known nothing about it. No more have this crowd of German and Italian scholars, very learned and, as I think, very Catholic, who admit with Copernicus that the earth is turned. Is it possible that after a lapse of time as considerable as this, we have nothing more than a rumour of such an event? I find it hard to believe, since nothing more definite has come from Italy. Definitions of this sort ought above all to be published in the universities, where the learned men are, to whom the danger of such an opinion is very great." Galileo, meanwhile, had retired to Florence and devoted himself to mechanical science, of which his work is the foundation, though constantly harassed by much ill health and many family perplexities. At the advice of his friends, he allowed the attacks on the Copernican doctrine to go unanswered, till, with the accession to the papacy in 1623 of Cardinal Barberini as Urban VIII, a warm admirer and supporter of his, he thought relief was in sight. He was further cheered by a conversation Cardinal de Zollern reported having had with Pope Urban, in which His Holiness had reminded the Cardinal how he, the Pope, had defended Copernicus in the time of Paul V, and asserted that, out of just respect owed to the memory of Copernicus, if he had been Pope then, he would not have permitted his opinion to be declared heretical. Feeling that he now had friends in power, Galileo began his great work, Dialogo sopra I due sistemi massimi del mundo, a dialogue in 4 days, in which 3 interlocutors discuss the arguments for and against the Copernican theory, though coming to no definite conclusion. Sagredo was an avowed Copernican and Galileo's spokesman. Salviati was open-minded, and the peripatetic was Simplicio, appropriately named for the famous Sicilian 6th-century commentator on Aristotle. In 1630 he brought the completed manuscript to Riccardi, master of the Sacred Palace, for permission to print it in Rome. After much reading and rereading of it, both by Riccardi and his associate Father Visconti, permission was at length granted, on condition that he insert a preface and a conclusion practically dictated by Riccardi, emphasizing its hypothetical character. The Pope's own argument was to be used. God is all-powerful. All things are therefore possible to him. Ergo, the tides cannot be adduced as a necessary proof of the double motion of the earth without limiting God's omnipotence, which is absurd. Galileo returned to Florence in June with the permission to print his book in Rome. Meanwhile, the plague broke out. He decided to print it in Florence instead, and on writing to Riccardi for that permission, the latter asked for the book to review it again. The times were too troublesome to risk sending it, so a compromise was finally effected. Galileo was to send the preface and conclusion to Rome, and Riccardi agreed to instruct the Inquisitor at Florence as to his requirements, and to authorize him to license the book. The parts were not returned from Rome till July 1631, and the book did not appear till February of the following year, when it was published at Florence with all these licenses, both the Roman and the Florentine ones. The Dialogo was in Italian, so that all could read it. It begins with an outline of the Aristotelian system, then points out the resemblances between the Earth and the planets. The second day demonstrates the daily rotation of the Earth on its axis. The next claims that the necessary stellar parallax is too minute to be observed and discusses the Earth's annual rotation. The last seeks to prove this rotation by the ebb and flow of the tides. It is a brilliant book and received a great reception. The authorities of the Inquisition at once examined it and denounced Galileo, April 17, 1633, because, in it, he had not merely taught and defended the condemned doctrine, but was gravely suspected of firm adherence to this opinion. Other charges made against him were that he had printed the Roman licenses without the permission of the congregation, that he had printed the preface in different type, so alienating it from the body of the book, and had put the required conclusion into the mouth of a fool, Simplicio, that in many places he had abandoned the hypothetical treatment and asserted the forbidden doctrine, and that he had dealt indecisively with the matter, though the congregation had specifically condemned the Copernican doctrine as contrary to the express words of the Scripture. The Pope became convinced that Galileo had ridiculed him in the character of Simplicio, to whom Galileo had naturally enough assigned the Pope's syllogistic argument. On the 23rd of December, he ordered the Inquisitor of Florence to notify Galileo, in the presence of concealed notary and witnesses in case he were recusant, to come to Rome and appear before the sacred congregation before the end of the next month. The publication and sale of the Dialogo meanwhile being stopped at great financial loss to the printer. Galileo promised to obey, but he was nearly 70 years old, and so much broken in health that a long, difficult journey in the approaching winter seemed a great and unnecessary hardship, especially as he was loath to believe that the church authorities were really hostile to him. Delays were granted him till the Pope in December finally ordered him to be in Rome within a month. The Florentine Inquisitor replied that Galileo was in bed so sick that 3 doctors had certified that he could not travel except at serious risk to his life. This certificate declared that he suffered from an intermittent pulse, from enfeebled vital faculties, from frequent dizziness, from melancholia, weakness of the stomach, insomnia, shooting pains, and serious hernia. The answer that the Pope made to this was to order the Inquisitor to send, at Galileo's expense, a commissary and a doctor out to his villa to see if he were feigning illness. If he were, he was to be sent, bound and in chains, to Rome at once. If were really too ill to travel, then he was to be sent in chains as soon as he was convalescent and could travel safely. Galileo did not delay after that any longer than he could help, and set out for Rome in January in a litter supplied by the Tuscan Grand Duke. The journey was prolonged by quarantine, but upon his arrival, February 13, 1633, he was welcomed into the palace of Niccolini, the warm-hearted ambassador of the Grand Duke. 4 times was the old man summoned into the presence of the Holy Office, though never when the Pope was presiding. In his first examination, held on the 12th of April, he told how he thought he had obeyed the decree of 1616, as his Dialogo did not defend the Copernican doctrine, but rather confuted it, and that, in his desire to do the right, he had personally submitted the book while in manuscript to the censorship of the Master of the Sacred Palace, and had accepted all the changes he and the Florentine Inquisitor had required. He had not mentioned the affair of 1616 because he thought that order did not apply to this book, in which he proved the lack of validity and of conclusiveness of the Copernican arguments. With remarkable, in fact unique consideration, the Holy Office then assigned Galileo to a suite of rooms within the prisons of the Holy Office, allowed him to have his servant with him, and to have his meals sent in by the ambassador. On the 30th, after his examination, they even assigned as his prison the ambassador's palace, out of consideration for his age and ill health. In his second appearance, April 30, Galileo declared he had been thinking matters over after rereading his book, which he had not read for 3 years, and freely confessed that there were several passages which would mislead a reader unaware of his real intentions into believing the worse arguments were the better, and he blamed these slips upon his vain ambition and delight in his own skill in debate. He thereupon offered to write another day or two more for the Dialogo, in which he would completely refute the 2 strong Copernican arguments based on the sun's spots and on the tides. 10 days later, at his third appearance, he presented a written statement of his defence, in which he claimed that the phrase vel quovis modo docere was wholly new to him, and that he had obeyed the order given him by Cardinal Bellarmine over the latter's own signature. However, he would make what amends he could, and begged the cardinals to consider his miserable bodily health and his incessant mental trouble for the past 10 months, the discomforts of a long, hard journey at the worst season, when 70 years old, together with the loss of the greater part of the year, and that therefore such suffering might be adequate punishment for his faults, which they might condone to failing old age. Also he commended to them his honour and reputation against the calumnies of his ill-wishers who seek to detract from his good name. To such a plight was the great man brought, but the end was not yet. Nearly a month later, June 16, by order of the Pope, Galileo was once again interrogated, this time under threat of torture. Once again he declared the opinion of Ptolemy true and indubitable, and said he did not hold and had not held this doctrine of Copernicus after he had been informed of the order to abandon it. As for the rest, he added, "I am in your hands. Do with me as you please. I am here to obey." Then, by the order of the Pope, ensued Galileo's complete abjuration on his knees in the presence of the full congregation, coupled with his promise to denounce other heretics, i.e. Copernicans. In addition, because he was guilty of the heresy of having held and believed a doctrine declared and defined as contrary to the Scriptures, he was sentenced to formal imprisonment at the will of the congregation, and to repeat the 7 penitential psalms every week for 3 years. At Galileo's earnest request, his sentence was commuted almost at once to imprisonment, first in the Archiepiscopal Palace in Siena from June 30 to December 1st, then in his own villa at Arcetri outside Florence, though under strict orders not to receive visitors but to live in solitude. In the spring, his increasing illness occasioned another request for greater liberty in order to have the necessary visits from the doctor. But on March 23, 1634, this was denied him with a stern command from the Pope to refrain from further petitions lest the sacred congregation be compelled to recall him to their prisons in Rome. The rule forbidding visitors seems not to have been rigidly enforced all the time, for Milton visited him, a prisoner of the Inquisition, in 1638. Yet Father Castelli had to write to Rome for permission to visit him to learn his newly invented method of finding longitude at sea. When in Florence on a very brief stay to see his doctor, Galileo had to have the especial consent of the Inquisitor in order to attend Mass at Easter. He won approval from the Holy Congregation, however, by refusing to receive some gifts and letters brought him by some German merchants from the Low Countries. He was then totally blind, but he dragged out his existence until January 8, 1642, the year of Newton's birth, when he died. As the Pope objected to a public funeral for a man sentenced by the Holy Office, he was buried without even an epitaph. The first inscription was made 31 years later, and in 1737 his remains were removed to Santa Croce after the congregation had first been asked if such action would be unobjectionable. Pope Urban had no intention of concealing Galileo's abjuration and sentence. Instead, he ordered copies of both to be sent to all inquisitors and papal nuncios that they might notify all their clergy and especially all the professors of mathematics and philosophy within their districts, particularly those at Florence, Padua, and Pisa. This was done during the summer and fall of 1633. From Vilna in Poland, Cologne, Paris, Brussels, and Madrid, as well as from all Italy, came the replies of the papal officials stating that the order had been obeyed. He evidently intended to leave no ground for a remark like that of Fromundus about the earlier condemnation. Galileo was thus brought so low that the famous remark, "Eppur si muove," legend reports him to have made as he rose to his feet after his abjuration, is incredible in itself, even if it had appeared in history earlier than its first publication in 1761. But his discoveries and his fight in defense of the system did much both to strengthen the doctrine itself and to win adherence to it. The appearance of the moon as seen through a telescope destroyed the Aristotelian notion of the perfection of heavenly bodies. Jupiter's satellites gave proof by analogy of the solar system, though on a smaller scale. The discovery of the phases of Venus refuted a hitherto strong objection to the Copernican system, and the discovery of the spots on the Sun led to his later discovery of the Sun's axial rotation, another proof by analogy of the axial rotation of the Earth. Yet he swore the Ptolemaic conception was the true one. The abjuration of Galileo makes a pitiful page in the history of thought and has been a fruitful source of controversy for nearly 3 centuries. He was unquestionably a sincere and loyal Catholic, and, accordingly, submitted to the punishment decreed by the authorities. But in his abjuration he plainly perjured himself, however fully he may be pardoned for it because of the extenuating circumstances. Had he not submitted and been straitly imprisoned, if not burned, the world would indeed have been the poorer by the loss of his greatest work, the Dialoghi delle Nuove Scienze, which he did not publish until 1636. Even more hotly debated has been the action of the Congregation in condemning the Copernican doctrine and silencing Galileo as a heretic for upholding it. Though both Paul V and Urban VIII spurred on these actions, neither signed either the decree or the sentence, nor was the latter present at Galileo's examinations. Pope Urban would prefer not so openly to have changed his position from that of tolerance to his present one of active opposition, caused partly by his piqued self-respect and partly by his belief that this heresy was more dangerous even than that of Luther and Calvin. It is a much mooted question whether the infallibility of the Church was involved or not. Though the issue at stake was not one of faith, nor were the decrees issued by the Pope ex cathedra, but by a group of cardinals, a fallible body, yet they had the full approbation of the popes, and later were published in the Index, preceded by a papal bull excommunicating those who did not obey the decrees contained therein. It seems to be a matter of the letter as opposed to the spirit of the law. De Morgan points out that contemporary opinion, as represented by Fromundus, an ardent opponent of Galileo, did not consider the decree of the Index or of the Inquisition as a declaration of the Church, a position which Galileo himself may have held, thus explaining his practical disregard of the decree of 1616 after he was persuaded the authorities were more favourably disposed to him. But Monsieur Martin, himself a Catholic, thinks that theoretically the congregations could punish Galileo only for disobedience of the secret order. But even so, his book had been examined and passed by the official censors. When the Index was revised under Pope Benedict XIV in 1757, largely through the influence of the Jesuit astronomer Boscovich, so it is said, the phrase prohibiting all books teaching the immobility of the sun and the mobility of the earth was omitted from the decrees. But in 1820, the master of the Sacred Palace refused to permit the publication in Rome of a textbook on astronomy by Canon Seteli, who thereupon appealed to the congregations. They granted his request in August, and 2 years later issued a decree approved by Pope Pius VII, ordering the master of the Sacred Palace in future not to refuse license for publication of books dealing with the mobility of the earth and the immobility of the sun, according to the common opinion of modern astronomers, on that ground alone. The next edition of the Index Librorum Prohibitorum in 1835 did not contain the works of Copernicus, Galileo, Foscarini, Astunica, and Kepler, which had appeared in every edition up to that time since their condemnation in 1616. Kepler's in 1619. Chapter 6. The Opposition and Their Arguments. The Protestant leaders had rejected the Copernican doctrine as contrary to the Scriptures. The Roman congregations had now condemned Galileo for upholding this doctrine after they had prohibited it for the same reasons. These objections are perhaps best summarized in the open letter Foscarini wrote to the general of his order, the Carmelites, at Naples in January 1615, the letter that was absolutely prohibited by the Index in March 1616. He gave these arguments and answered them lest, as he said, whilst otherwise the opinion is favoured with much probability, it be found in reality to be extremely repugnant, as at first sight it seems, not only to physical reasons and common principles received on all hands, which cannot do so much harm, but also, which would be of far worse consequence, to many authorities of sacred Scripture. Upon which account many at first looking into it explode it as the most fond paradox and monstrous capriccio that ever was heard of. Yet many modern authors, he says further on, are induced to follow it, but with much hesitancy and fear, in regard that it seemeth in their opinion so to contradict the Holy Scriptures that it cannot possibly be reconciled to them. Consequently, Foscarini argued that the theory is either true or false. If false, it ought not to be divulged. If true, the authority of the sacred Scriptures will not oppose it. Neither does one truth contradict another. So, he turned to the Bible. He found that 6 groups of authorities seemed to oppose this doctrine. 1. Those stating that the earth stands fast, as Ecclesiastes 1:4. 2. Those stating that the sun moves and revolves, as in Psalm 19, Isaiah 28, and the miracle in Joshua 10:12-14. 3. Those speaking of the heaven above and the earth beneath, as in Joel 2. Also, Christ came down from heaven. 4. Those authorities who place hell at the center of the world, a common opinion of divines, because it ought to be in the lowest part of the world, that is, at the center of the sphere. Then, by the Copernican hypothesis, hell must either be in the sun, or, if in the earth, if the earth should move about the sun, then hell within the earth would be in heaven, and nothing could be more absurd. 5. Those authorities opposing heaven to earth and earth to heaven, as in Genesis 1, Matthew 6, etc. Since the two are always mutually opposed to each other, and heaven undoubtedly refers to the circumference, earth must necessarily be at the center. 6. Those authorities rather of the fathers and divines than of the sacred scriptures, who declare that after the day of judgment the sun shall stand immovable in the east and the moon in the west. Foscarini then lays down in answer 6 maxims, the first of which is that things attributed to God must be expounded metaphorically according to our manner of understanding and of common speech. The other maxims are more metaphysical, as that everything in the universe, whether corruptible or incorruptible, obeys a fixed law of its nature. So, for example, fortune is always fickle. In concluding his defense, he claims, among other things, that the Copernican is a more admirable hypothesis than the Ptolemaic, and that it is an easy way into astronomy and philosophy. Then he adds that there may be an analogy between the 7-branched candlestick of the Old Testament and the 7 planets around the sun, and possibly the arrangement of the seeds in the Indian fig, in the pomegranate, and in grapes is all divine evidence of the solar system. With such an amusing reversion to medieval analogy, his spirited letter ends. Some or all of these scriptural arguments appear in most of the attacks on the doctrine even before its condemnation by the Index in 1616 was widely known. Besides these objections, Aristotle's and Ptolemy's statements were endlessly repeated with implicit faith in their accuracy. Even Sir Francis Bacon, with all his modernity of thought, failed in this instance to recognize the value of the new idea and, despite his interest in Galileo's discoveries, harked back to the time-honored objections. At first mild in his opposition, he later became emphatically opposed to it. In the Advancement of Learning, 1604, he speaks of it as a possible explanation of the celestial phenomena according to astronomy, but as contrary to natural philosophy. Some 15 years later, in the Novum Organon, he asserts that the assumption of the Earth's movement cannot be allowed, for, as he says in his Thema Celi, at that time he considered the opinion that the Earth is stationary the truer one. Finally, in his De Augmentis Scientiarum, he speaks of the old notions of the solidity of the heavens, etc., and adds, "It is the absurdity of these opinions that has driven men to the diurnal motion, which I am convinced is most false." He gives his reasons in the Descriptio Globi Intellectualis. In favor of the Earth as the center of the world, we have the evidence of our sight and an inveterate opinion, and most of all this, that as dense bodies are contracted into a narrow compass and rare bodies are widely diffused, and the area of every circle is contracted to the center, it seems to follow, almost of necessity, that the narrow space about the middle of the world be set down as the proper and peculiar place for dense bodies. The Sun's claims to such a situation are satisfied through having 2 satellites of its own, Venus and Mercury. Copernicus's scheme is inconvenient. It overloads the Earth with a triple motion. It creates a difficulty by separating the Sun from the number of the planets with which it has much in common, and the introduction of so much immobility into nature, and making the Moon revolve around the Earth in an epicycle, and some other assumptions of his, are the speculations of one who cares not what fictions he introduces into nature, provided his calculations answer. The total absence of all reference to the scriptures is the unique and refreshing part of Bacon's thought. All the more common arguments against the diurnal rotation of the Earth are well stated in an interesting little letter by Thomas Fayens, or Finus, a professor at the School of Medicine in the University of Louvain. Thus, Catholic, Protestant, and unbeliever, Fayens, Melanchthon, Bacon, and Baudin, all had recourse to the same arguments to oppose this seemingly absurd doctrine. Freudmont, or Fromundus, the good friend and colleague of Fayens at Louvain, was also much interested in these matters, so much so that some thought he had formally accepted the Copernican doctrine and only fled back into the camp of Aristotle and Ptolemy through terror at the decree of the S Congregation of Cardinals. His indignant denial of this imputation of turncoat in 1634 is somewhat weakened by reference to his Saturnalite Conae, in which he suggests that, if the Copernican doctrine is admitted, then hell may be in the sun at the center of the universe rather than in the earth, in order to be as far as possible from paradise. He also refers in his De Cometa to the remark of Justus Lipsius that this paradox was buried with Copernicus, saying, "You are mistaken, O noble scholar. It lives, and it is full of vigor even now among many," thus apparently not seeing serious objection to it. Monsieur Montchamp summarizes Freudmont's point of view as against Aristotle and Ptolemy, half for Copernicus, and wholly for Tycho Brahe. Freudmont's best-known books are the two he wrote in answer to a defense of the Copernican position, first by Philip Landsberg, then by his son. The Ant Aristarchus sive orbis terra immobilis liber unicis in quo decretum s congregationis SRE Cardinal on 1616 adversus Pythagorico Copernicanus editum defenditor appeared in 1631 before Galileo's condemnation. The Jesuit Cavalieri wrote to Galileo in May about it thus: "I have run it through, and verily it states the Copernican theory and the arguments in its favor with so much skill and efficacy that he seems to have understood it very well indeed. But he refutes them with so little force that he seems rather to be of an opinion contrary to that expressed in the title of his book. I have given it to Monsieur César. If you wish it, I will have it sent to you. The arguments he brings against Copernicus are those you have so masterfully stated and answered in your Dialogo." Nearly a year later, Galileo wrote to Gassendi and Diodati that he had received this book a month before, and, although he had been unable to read much of it on account of his eye trouble, it seemed to him that of all the opponents of Copernicus whom he had seen, Fromundus was the most sensible and efficient. Again, he wrote in January 1633, regretting that he had not seen it till 6 months after he had published his dialogues, for he would have both praised it and commented upon certain points. As for Fromundus, who, however, shows himself to be a man of great talent, I wish he had not fallen into what seems to me a truly serious error, although a rather common one, in order to refute the Copernican opinion of beginning by poking scorn and ridicule at those who consider it true, and then, what seems to me still less becoming, of basing his attack chiefly on the authority of the Scriptures, and finally of deducing from this that in this respect it is an opinion little short of heretical. To argue in this way is clearly not praiseworthy, for, as Galileo goes on to show, if the Scriptures are the word of God, the heavens themselves are his handiwork. Why is the one less noble than the other? Freudmont replied in 1633 to Landsberg's reply with his second attack, Vesta, sive ant Aristarchi vindex, in which he laid even more emphasis upon the theological and scriptural objections. Yet, in ignorance of Galileo's condemnation, he considers the charge of heresy too strong. The partisans of this system do not, after all, disdain the authority of the Scriptures, although they appear to interpret it in a way rather in their favor. He also, and rightly, denies the existence at that time of any conclusive proof. In spite of Freudmont's position, the University of Louvain was not cordial in its response to the papal nuncio's announcement in September 1633 of Galileo's abjuration and sentence, in marked contrast to the reply sent by the neighboring University of Douai. The latter body, in a letter signed by Matthias Kellerson, declared the condemned theory should be discarded and hissed from the schools, and that in the English college there in Douai this paradox never had been approved and never would be, but had always been opposed and always would be. This opposition in the universities in Belgium continued throughout the century to be based not so much on scientific grounds as upon the Bible. This may be seen in the manuscript reports of lectures in physics and astronomy given at Liège in 1662 and at Louvain between 1650 and 1660, though one of these does not mention the decree of 1616. The General Congregation of the Society of Jesus in 1650 drew up a list of the propositions proscribed in their teaching, though, according to M. Montchamp, himself a Catholic, not thereby implying a denial of any probability they might have. The 35th proposition ran, Terra movetur motu diurno, planetae tanquam viventia, moventa ab intrinsico, firmamentum stat. The Jesuit astronomer Taquet in his textbook respected this decision, acknowledging that no scientific reason kept him from defending the theory, but solely his respect for the Christian faith. One of the pupils of the Jesuits revolted, however. Martin van Welden, appointed professor of mathematics at Louvain in 1683, debated a series of theses in January 1691. The second read, Indubitum est systema Copernici de planetarum motu circa sole, inter quos merito terra sensitur. His refusal to alter the wording except to change indubitum to certum brought on a stormy controversy within the faculty which eventually reached the Council of Brabant and the papal nuncio at Brussels. The professor finally submitted, though he was not forbidden to teach the Copernican system, nor did the faculty affirm its falsity, merely that it was contrary to the Roman decree. The professor reopened the matter with a similar thesis in July, thereby arousing a second controversy that this time reached even the Privy Council. Once more he submitted, but solely with an apology for having caused a disagreement. His new theses in 1695 contained no explicit mention of the Copernican system. At least he had learned tact. The absorption of the German states in the 30 Years' War may account for the apparent absence there of Copernican discussion until after the Peace of Westphalia. A certain Georgius Ludovicus Agricola gave a syllogistic refutation of the doctrine as his disputation at the University of Wittenberg in 1665. While he acknowledged its ingenuity, he preferred to it the noblest, truest, and divinely inspired system of Tycho Brahe. The 4 requirements of an acceptable astronomical hypothesis, according to this student, are 1. That it suit all the observations of all the ages. 2. That, as far as possible, it be simple and clear. 3. That it be not contrary to the principles of physics and optics. 4. That it be not contrary to the Holy Scriptures. As the Copernican theory does not meet all these tests, it is unsatisfactory. Incidentally, he considers it ridiculous to include the Earth among the planets, because then we would be living in heaven, forsooth, since we would be in a star. He decides, finally, that the decree of March 1616 condemning the Copernican opinion was not unjust, nor was Galileo unfairly treated. 2 years later appeared a textbook at Nuremberg by a Jesuit father based on the 12th century Sacrobosco treatise and without a single reference, so far as I could find, to Copernicus. Another publication of the same year was a good deal more up-to-date. This was a kind of catechism in German by Johann Henrik Voigt, explaining for the common people various scientific and mathematical problems in 100 questions and answers. He himself, a royal Swedish astronomer, obviously preferred the Tychonic system, but he left his reader free to choose between that and the Copernican one, both of which he carefully explained. He made an interesting summary in parallel columns of the arguments for and against the Earth's motion, which it seems worthwhile to repeat as an instance of what the common people were taught. Reasons for asserting the Earth is motionless. 1. David in Psalm 89. God has founded the earth and it shall not be moved. 2. Joshua bade the sun stand still, which would not be notable were it not already at rest. 3. The earth is the heaviest element, therefore it more probably is at rest. 4. Everything loose on the earth seeks its rest on the earth. Why should not the whole earth itself be at rest? 5. We always see half the heavens and the fixed stars also in a great half circle, which we could not see if the earth moved, and especially if it declined to the north and south. 6. A stone or an arrow shot straight up falls straight down, but if the earth turned under it from west to east, it must fall west of its starting point. 7. In such revolutions, houses and towers would fall in heaps. 8. High and low tide could not exist. The flying of birds and the swimming of fish would be hindered, and all would be in a state of dizziness, and similarly on both sides. Reasons for the belief that the earth is moved. 1. The sun, most excellent, the greatest and the midmost star, rightly stands still like a king, while all the other stars with the earth swing round it. 2. That you believe that the heavens revolve is due to ocular deception, similar to that of a man on a ship leaving shore. 3. That Joshua bade the sun stand still, Moses wrote for the people in accordance with the popular misconception. 4. As the planets are each a special created thing in the heavens, so the earth is a similar creation and similarly revolves. 5. The sun fitly rests at the center as the heart does in the middle of the human body. 6. Since the earth has in itself its especial centrum, a stone or an arrow falls freely out of the air again to its own centrum, as do all earthly things. 7. The earth can move 5 miles in a second more readily than the sun can go 40 miles in the same time. Another writer preferring the Tychonic scheme was Longomontanus, whose Astronomica Danica, Amsterdam 1640, upheld this theory because it obviates the absurdities of the Copernican hypothesis and most aptly corresponds to celestial appearances, and also because it is midway between that and the Ptolemaic one. Even though he speaks of the apparent motion of the sun, he attributed diurnal motion to the heavens and believed the earth was at the center of the universe because, 1. From the account of the creation, the heaven and the earth were first created, and what could be more likely than that the heavens should fill the space between the center, the earth, and the circumference. 2. And because of the incredibly enormous interval between the sphere of the fixed stars and the earth necessitated by Copernican doctrine. The high water mark of opposition after Galileo's condemnation was reached in the Almagestum Novum, Bologna 1651, by Father Riccioli of the Society of Jesus. It was the authoritative answer of that order, the leaders of the Church in matters of education, to the challenges of the literary world for a justification of the condemnation of the Copernican doctrine and of Galileo for upholding it. Father Riccioli had been professor of philosophy and of mathematics for 6 years, and of theology for 10, when, by order of his superiors, he was released from his lectureship to prepare a book containing all the material he could gather together on this great controversy of the age. He wrote it, as he himself said, as an apologia for the sacred congregation of the cardinals who officially pronounced these congregations, not so much because I thought such great height and eminence needed this at my hands, but especially in behalf of Catholics. Also out of the love of truth to which every non-Catholic even should be persuaded, and from a certain notable zeal and eagerness for the preservation of the sacred scriptures intact and unimpaired. And lastly, because of that reverence and devotion which I owe from my particular position toward the Holy, Catholic and Apostolic Church. This monumental work, the most important literary production of the Society in the 17th century, is abundant witness to Riccioli's remarkable erudition and industry. Nearly 1/5 of the total bulk of the 2 huge volumes is devoted to a statement of the Copernican controversy. This is prefaced by a brief account of his own theory of the universe, the invention of which is another proof of the ability of the man, for his scientific training prevented his acceptance of the Aristotelian Ptolemaic theory in the light of Galileo's discoveries. His position as a Jesuit and a faithful son of the Church precluded him from adopting the system condemned by its representatives, and Tycho Brahe's scheme was not wholly to his liking. Therefore, he proposed an adaptation of the last named, more in accordance, as he thought, with the facts. Where Tycho had all the planets except the Earth and the Moon encircle the Sun, and that in turn, together with the Moon and the sphere of the fixed stars, sweep around the Earth as the center of the universe, Riccioli made only Mars, Mercury, and Venus encircle the Sun. Mars with an orbit the radius of which included the Earth within its sweep, the other 2 planets with orbital radii shorter than that of the Sun, and so excluding the Earth. This he did, 1, because both Jupiter and Saturn have their own kingdoms in the heavens, and Mars, Mercury, and Venus are but satellites of the Sun. 2, because there are greater varieties of eccentricity among these 3 than the other 2. 3, because Saturn and Jupiter are the greatest planets and with the sphere of the fixed stars move more slowly. 4, Mars belongs with the Sun because of their related movements, and 5, because it is likely that one of the planets would have much in common both with Saturn and Jupiter and with Mercury and Venus also. Then he takes up the attack upon the Copernican doctrine. Monsieur Delambre summarizes and comments upon 57 of his arguments against it, and Riccioli himself claims to have stated 40 new arguments in behalf of Copernicus and 77 against him. But these sound somewhat familiar to the reader of anti-Copernican literature, as, for instance, which is more natural, straight or circular movement? Or the Copernican argument that movement is easier if the object moved is smaller involves a matter of faith, since it implies a question of God's power, for to God all is alike, there is no hard nor easy. Although diurnal movement is useful to the Earth alone, and so, according to the Copernicans, the Earth should have the labor of it, Riccioli argues that everything was created for man. Let the stars revolve around him. The Sun may be nobler than the Earth, but man is nobler than the Sun. If the Earth's movement were admitted, Ptolemy's defense would be broken down through the elimination of the epicycles of the superior planets. Here, if ever, the Copernicans appear to score, as Riccioli himself admits, but he calls to his aid Tycho Brahe and the Bible. To invoke such aids is to avow his defeat, is Monsieur Delambre's comment on this point. There are many more arguments, of which the foregoing are but instances, chosen more or less at random, but no one of them is of a special weight or novelty. To strengthen his case, Riccioli listed the supporters of the heliocentric doctrine throughout the ages with those of the opposite view. If a man's fame adds to the weight of his opinion, the modern reader will be inclined to think the Copernicans have the best of it, for, omitting the ancients, most of those opposing it are obscure men. In favor of the Copernican doctrine, Copernicus, Rheticus, Maestlin, Kepler, Rothman, Galileo, Gilbert, diurnal motion, Foscarini, Didacus Stunica, Ismael Bulialdus, Jacob Landsberg, Peter Herregonus, Gassendi, but submits his intellect captive to the church decrees. Descartes inclines to this belief. A. L. Politianus, Bruno. Against the hypothesis of the Earth's movement, Aristotle, Ptolemy, Theon the Alexandrine, Regiomontanus, Alfraganus, Macrobius, Cleomedes, Petrus Aliacensis, George Buchanan, Maurolycus, Clavius, Barosius, Michael Neander, Telesius, Martinengus, Justus Lipsius, Scheiner, Tycho, Tasso, Scipio Claremontius, Michael Inkofer, Fromundus, Jacob Ascaricius, Julius Caesar Legala, Tanner, Bartholomeus Amicus, Antonio Rocci, Marinus Masenius, Polacco, Kircher, Spinella, Pineda, Laurinus, Mastrius, Belutris, Pontius, Delphinus, Elphantutius. Riccioli nevertheless viewed the Copernican system with much sympathy. After a full statement of it, he comments, "We have not yet exhausted the full profundities of the Copernican hypothesis, for the deeper one digs into it, the more ingenious and valuable subtleties may one unearth." Then he adds that the greatness of Copernicus has never been sufficiently appreciated, nor will it be. The man who accomplished what no astronomer before him had scarcely been able even to suggest without an insane machinery of spheres, for by a triple motion of the earth he abolished epicycles and eccentrics. What before so many atlases could not support, this one Hercules has dared to carry. Would that he had kept himself within the limits of his hypothesis. His conclusions seem to show that only his position as a Jesuit restrained him from being a Copernican himself. 1. If the celestial phenomena alone are considered, they are equally well explained by the two hypotheses, Ptolemaic and Copernican. 2. The physical evidence as explained in the two systems, with the exception of percussion and the speed of bodies driven north or south and east or west, is all for immobility. 3. One might waver indifferently between the two hypotheses aside from the witness of the Scriptures, which settles the question. 4. There are in addition plenty of other motives besides scriptural ones for rejecting this system. But with the scriptural evidence he adduces the decree of the Index under Paul V against the doctrine and the sentence of Galileo, so that the sole possible conclusion is that the earth stands by nature immobile in the center of the universe, and the sun moves around it with both a diurnal and an annual motion. Even this great book was as insufficient to stop the criticism of the action of the congregations as it was to stop the spread of the doctrine. So, once again, the father took up the cudgels in defense of the Church. The full title of his Apologia runs, "An Apologia in behalf of an argument from physical mathematics against the Copernican system, directed against that system by a new argument from the reflex motion of falling weights." Venice, 1669. He states in this that his Almagestum Novum had received the approbation of professors of mathematics at Bologna, of one at Pisa, and of another at Padua, and he quotes the conclusion from Nicetus Orthodoxus, a diatribe by Julius Turinus, doctor of mathematics, philosophy, medicine, law, and Greek letters, that the sun is revolved by diurnal and by annual motion, and that the earth is at rest, I firmly hold, infallibly believe, and openly confess, not because of mathematical reasons, but solely at the command of faith, by the authority of the Scriptures and the nod of approval of the Roman See, whose rules laid down at the dictation of the Spirit of truth, may I, as befits everyone, uphold as law. Riccioli further on proceeds to answer his objectors, declaring that the Church did not decide ex cathedra that the Scripture concerning movement should be interpreted literally, that the censure was laid by qualified theologians and approved by eminent cardinals, and was not merely provisional, nor for the time being absolute, since the contrary could never be demonstrated, and that, while it was the primary intent of the inquisitors to condemn the opinion as heretical and directly contrary to the Scriptures, they added that it was absurd and false also in philosophy, in order not to avert any objections which could be on the side of philosophy or astronomy, but only lest anyone should say that Scripture is opposed to philosophy. These answers are indicative of the type of criticism with which the Church had to cope even at that time. This has been When the Sun Became the Center, How Copernicus Transformed Astronomy, written by Dorothy Stimson, narrated by Jason Zenobia. Copyright 2018 by MSAC Philosophy Group. Production copyright 2018 by MSAC Philosophy Group.